processes. It's
still moving or? Yes. But normally this goes. This is the first one, right? Oh, this one? Oh. Oh, here we go. I think we need to stay like this or go like this. Okay.
So, good morning, everyone. Good morning, the audience that participates online through the various streaming options and broadcasting. Welcome to the Code for Earth Final Day event in Bologna. We had a very, very interesting journey throughout the last couple of months, especially the participants and the mentors had a nice coding phase. I hope you had a nice coding summer. And before we dive into Code for Earth in detail and into the presentations, I would like to give the stage to Stijn Vermooten, our section head for user engagement and outreach. And he will set the scene and talk about ECMWF because we are heavily supported. It's an ECMWF program, and he will explain or talk about what ECMWF is and what we are doing at the data center. Stijn, the floor is yours.
Good morning, all. Such a delight to be here in this beautiful Bologna. Welcome to everyone who follows online. Welcome to all the participants for this 2023 edition. Welcome to all the mentors who guided all the participants through this very exciting process. So I will give a brief introduction to ECMWF. I have 50 minutes, so I want to focus on a couple of things which to give you some background on who ECMWF is and why we are there. So we have been established nearly 40 years ago, 50 years ago in 75. We have 23 member states, 12 cooperating states, and more than 400 staff. So it's a growing activity and it's a true international organization embedded in Europe. On one side, we are an operational service. So we operate the numerical weather predictions, the high resolution ensembles, but also ensemble forecast on a daily basis, 4 times a day. We support NWP with coupled models and businesses. On the other side, we also a research institute. Research is very essential to keep on experimenting and to continue to improve our models. But research also means reforecasting in climate reanalysis. We operate 2 Copernicus services, the Climate Change Service and the Atmosphere Monitoring Service on behalf of the European Commission. But we also are the computing center for the Copernicus Emergency Management Service for floods and fires. So this gives us a very good foundation to do a lot of additional things. And this brought us also to Destination Earth, which is more looking into Earth system modeling. And with this new ambitious program, we operate 2 additional twins and a digital twin engine on which I will elaborate a little bit more later on. So ECMWF really stands for producing cutting-edge science and world-leading weather predictions and monitoring of the Earth system in close collaboration with our member states and the European meteorological infrastructure for a safe and prosperous society. So now you have the catch line as well. So how do we work? It's based on a strategy, and the strategy is based on 3 pillars. Science and technology. I already mentioned the department, but it's very important. So we really want to stay the world leader in terms of weather and Earth system science. We do this based on cutting-edge technology and computational science for an NWP. So high-performance computing is very important. The second pillar is impacts. High-quality products which are fit for purpose, which serve the users, which are used, which are meaningful. And we need to make sure that everything is efficient and easy to access. So there's a lot of activities on this as well. And an organizational point, of course, is very important. It's really a staff-driven organization. So we have an efficient organization. We have scientists, we have computers specialists. We have people from different domains, and it's through these people that we are success. Now, let me give you some highlights. We are in Bologna, the Bologna data centers one. IFS, the latest cycle, move to open data policy, access to data, very important, training, Destination Earth, machine learning strategy, and Copernicus operational services. But let me start with Bologna. So our Ethos HPC has been is running in operation since last year, since the end of 2020, and we moved from Cray. This was a big operation because we had to bring the data center from Reading to Bologna. It also is a start of using a new system. So we moved from Cray to Ethos. We also operate here the data handling system, the Mars archive, the climate data store, and European weather cloud. And we have several people here in the room who can give you a lot of information on this. And tomorrow morning, if you subscribe, we will do a tour at the data center so you can learn more about this. The second key component is integrated forecasting system, IFS. It's really the core of what we're doing. And it has been a long-standing evolution with small incremental steps. So here you see each round where we go from an experimental suite to an operational suite. And through these incremental changes, both on physics, on solving bugs, on increasing resolution, on trying to improve our system, we advance more and more, by which we increase continuously the skill of our forecast. We are now at 4801, which came with a lot of significant changes, and in parallel, we're preparing for 4901. But we also see that besides this, we have to take into account the latest developments of machine learning. That's why in 21, we started with machine learning roadmap. And through this period, it has been a very steep learning curve with a lot of new activities, both internally. So we increased the number of people working on this, and you have several of our colleagues who are working on this here in the room who supported you also. We also saw there's a lot of interest in machine learning from the challenges which you have chosen. But we also see that through other activities done by other entities, we see that more and more of these activities are picked up. And this is very important that we communicate with them and that we see what they're doing, because it's thanks to those evolutions that we stay sharp, that we stay innovative, and that we advance ourselves as well. Through machine learning, we will be able to facilitate certain elements. Others will take more time. But it's also important to know that through this machine learning, we also see the added value of certain of our products, like ERA5 reanalysis is often used to train all these models. It comes from somewhere. It comes from us. It comes from ECMWF. It comes from Copernicus. We also see that thanks to machine learning, there are ways to do things cheaper, faster. And all these things are taken into account, and you will see more and more of these in the future. This also brings me to Destination Earth. So it's not only about weather, it's really moving into Earth system modeling. And we combine this rich structure of a high-performance computer and the ability to connect to other high-performance computers in Europe with the latest science on Earth system modeling, and then novel techniques like machine learning. We operate the digital twin engine. So that's an engine to develop digital twins, which are a digital representation of the Earth. And we operate two additional twins, one on extremes and one on climate adaptation. From an operational side, we are operating the Copernicus program. So the Copernicus program is an Earth observation program of the European Commission. Here you see the complete overview and the landscape of all the different components. The space component is, of course, something which gets a lot of visibility. ESA is running this. We are running the services, and the services are much closer to users. It's much more translating this Earth observation data, combine it with in situ data and models to derive user relevant outputs products. We operate the climate change service and the atmosphere monitoring service, as I mentioned, but also the emergency management service. And I know some of you also are working with this data directly to develop your applications. I want to put a highlight on C3S Global Reanalysis. It's one of our most important products. And with ERA5, we have a fully observed system global reanalysis for the atmosphere, land, and ocean waves. It has a massive use, and it enables us to have a snapshot of what the weather was at a daily basis from 1940 onwards. And it has a daily update with a delay of 5 days behind real time. So it's used as accurate and three-dimensional synoptic scale situation. So what I said, the weather of the day. We are able to compare a certain situation with climatology, so with a time scale of 30 years of climate of the past. It's used to estimate the variability of the mean state and obtain statistics for the climate-related extremes, which is very important also with climate change and seeing how things evolve in time. And often it's used to initialize, to do boundary conditions and to drive impact models, but also to train machine learning weather prediction models. The way the data is provided is through the CDS or the CADS, which is a new version now for the atmosphere and the climate change service. The new version will become operational in January 2024, so it will have a new interface, which makes it easier to explore. You have a CADS toolbox. You have a way to play with Jupyter notebooks, and some cloud resources are made available. And it's all way also to connect to Wikeo. So some of you may have the credentials to work with Wikeo. It's our contribution to Wikeo, which we do together with our colleagues at EUMETSAT, Mercator Océan, and EA. This also connects to our latest developments in software, from a software strategy. The first components which will be made available is an Earth kit for data and maps, where you can work with the data in a new way of based on GitHub and Jupyter Hub. The European Weather Cloud is another initiative. It's another initiative focused on cloud services. It's a joint initiative by ECMWF, EUMETSAT, and our member states. It's currently in operational ramp up, and September is a very important month because this month we aim to become operational. It's the last thing which we will make operational here in Bologna at our data center. It's also an important component of making the data available via cloud services. If you talk about data, we talk also about data accessibility from another point of view, which is open and free versus against payment, and we are moving towards an open data policy at ECMWF. It's very important also for a variety of applications, a variety of users, where Copernicus is already open and free. So this is by default, or weather data at ECMWF is not completely open and free at the moment, but we're gradually moving into this. So here you already see those things which are open and free. So we have the open shorts. Certain things are also available via Microsoft and Amazon. You have certain catalogs which are running via an open license. And for other things, we reduce the fees for some license types. So if you want more information on this, here you also have the links there. Then last but not least, training and learning. So you have been using our data, you have been working with it. I don't know to which extent you also did some learning activities and some trainings. But if you want to advance on this and you want to learn more, we have this platform here based on Moodle. It's a learning management system where you can really go into the details of forecast, research, data software, computing, Copernicus Climate Change Service, and all these things are made available for you to explore. So it's again open and free for your use, and you can advance on this if you want. And an example of this is the MOOC, which we have done run earlier this year. We had a massive online course on machine learning in weather and climate. The MOOC is closed, so it ran at the beginning of the year. But the data or the information is still available. So if you still want us to go and have a look at some videos, at some podcasts, it's still possible, and it's a very rich source of information. What I also want to highlight is that it was in partnership with IFAP, which is based here in Bologna. So it's interesting to see that we are now back in Bologna to present this. I think with this, I want to close, and I want to give the floor to Athena and Esperanza to start the presentation on the Code for Earth's challenges. Thank you.
Thank you very much, Stein. And we are preparing now for the intro. By the way, if you have from the audience here, if there are any questions, just raise your hand. Online, we are using Slido. And we are Good. So thanks again, Stein, for the introduction also to ECMWF and what we are doing at ECMWF, what data you can use. And now we are going for, what is Code for Earth? All of you here in the room, you have been involved in Code for Earth, but we would like to give an introduction or some explanation also for the audience that is following us online. And again, Esperanza Cuartero and we have been coordinating the program, and it has been a very interesting ride. And it was a pleasure and still is a pleasure to work with all of you. But what is Code for Earth? And this is mainly meant for, for the audience that is quite new. So it's a key innovation action run by ECMWF that engages external talents. So we welcome each summer experts and young scientists and talents from and developer teams from the Earth science community to work on challenges that have been identified by mentors that come from ECMWF, but also from external mentors. The program runs since 2018 and has produced over 35 open source software developments that are highly beneficial for the center and for the partnering organizations. We want to enhance also the visibility and the awareness of ECMWF to the outside world, but we also want to engage with people from the outside world to see what can be done differently, where is the innovation taking place, how we can mutually benefit from that. And the selected teams, they successfully finalize their challenges. They also get a 5,000 euro stipend. I just want to mention it for everyone who is listening from the outside. Here, the Code for Earth in the different phases and the steps. So we started early this year with a call for participation. That was in March. We had 2 webinars, Q&A webinars, and maybe some of the audience listening from the outside participated in the webinars as well. And then after receiving over 35 proposals, we had an evaluation process, which was not that easy because we had a lot of good proposals submitted. And together with the mentors, we came to a conclusion and ended up in 10 projects, 10 teams that we decided to support. And in May, the coding phase started. And this is when the mentors and the teams worked together over the last 4 months from May to end of August. I hope in a very exciting coding summer. And as said, now we are at the final day. We are here, we are in Bologna, and we will see the presentations today, the results from the teams. And we are really excited to see what happens, because my last insight was at the midterm webinar. So let's see. And I would like to hand over to Esperanza.
Mentorship. In this edition 2023, 29 mentors have taken part in Code for Earth, and we would like to take this moment to highlight and thanks for all of you for your dedication, for your free time and expertise and commitment to all the teams, because you have been guiding through 4 months of the coding phase for get these results, and the results are 10 projects and innovation and open source projects. So when expertise and talent couple, this is the result. The teams and the projects who go through this coding phase 2023 are part forecasting. You can see I'm not going to name all of them. Yeah. Part forecasting, benchmarking, surface classes, diffusion models and weather bench, TCRAC, deep reanalysis, atmospheric composition data set explorer, Sketchbook Earth, Illustrated Climate Chronicle, TropiDash. There was a comprehensive tropical cyclone hazard dashboard. Compression of geospatial data with varying information density on chat ECMWF. We are going to listen to you because you have panel results to share with everybody, to share a case. So this is your time.
Okay, there is one. Yeah, and generally, yeah, you have seen it's a plethora of its interesting topics that we run through today, these interesting presentations. And for everyone, just a heads up, there's stay tuned. After Code for Earth is before Code for Earth. So we are already working on the next edition, and you will see very likely in Q1 next year, 2024, we will start with the new edition. So don't miss the opportunity. And here are a couple of useful links. And to not keep you from the presentations, I would like to introduce or call the fire forecasting team. So the presenter is Markus Maywald, and the mentor is Johannes Kaiser, and I hand over to you.
Hey. Yeah, is it possible to activate the laser pointer for the slides? No, you need to enter the arrow. We don't have the remote. So the mouse show the front. Oh, you can, yes, you just click here. Oh, this is not PowerPoint. Okay, but I can, yes, it's. Okay. Good. So, good morning, everyone. For me, I'm Johannes Kaiser. I'm one of the mentors for the fire forecasting project. And first of all, I'd like to take the opportunity to thank ECMWF for setting up this program, providing the infrastructure, the computing infrastructure, but also the meeting infrastructure for people here, and to Atina and Esperanza for all the support and running. So that has been really essential that you two have been there along the way throughout. Then Robert will take over. Timo is also in the room from the forecasting team, and the other two people who are involved are Eva Maria Metz and Christopher Winkels, who unfortunately cannot join us today in person here. Let's get going. This project is called fire forecasting. So we are talking about wildfires. Why do we talk about wildfires in our context? We see that the smoke emitted from wildfires has a very large impact on air quality. And I imagine that every one of you this summer has seen this on the news in one form or another again and again and again. And particularly dominant were the wildfires in Canada this summer, but also Europe had some really extreme wildfire events, for example, in Greece. Stein mentioned the Atmosphere Copernicus Monitoring Service, CAMS. This is providing, besides many other things, but as core products, 5-day forecasts for atmospheric composition globally, and for air quality for the European domain. And here's an example from this forecast from the web page, which is the forecast of PM 2.5 for Bologna for this week, Tuesday to Friday. And you can see the color codes are thresholds determined by the European Environmental Agency. You see that we are in Bologna in a safe space. This is, there are no fires at the moment, but these PM levels can be affected by smoke from wildfires, of course. And that's what we're looking at in the project. So the smoke we need to, in order to do the forecast properly, we need to observe the fires from space and then determine from the observations where there are fires, how much smoke is being emitted, and put those in the model so that then we see in the forecast for Bologna whether there's a big plume coming through and people can adapt their behavior in case of really bad events. What is currently being done is we see the observed fires and then we use a 5-day persistence of the fire source. And here's an example of forecasts from the regional fire system for August in Greece here. That is the situation in terms of smoke, AOD, optical depth. So you can say how much smoke there is in the air. Over Greece on the 23rd of August, and that's the situation that was observed. And then there is a forecast initiated on the 25th, 26th, 27th, up to 27. And you could see that the smoke gets affected, but all the time the source stays at the one point there. And that may not be realistic because we know when there's a fire, it's going to extinguish eventually. So we are really producing false alarms with the system at the moment. And here the team comes in and they have developed a method with which I'm confident with the results that we will be able to reduce the number of false alarms within, say, the next half or full year of our forecast. So then I hand over to Robert. Thank you.
Yes, as Johannes mentioned, the current approach is persistent. So the assumption is that the fire for the next 5 days stays exactly the same as currently. And we want to forecast the wildfire intensity. So here you can see an example plot for how the fire intensity is normally measured between fire-related power, which is measured by satellites. And we want to use the GFAS, global. That's a step back. Yes, and we want to use the simulated system GFAS, which uses a satellite information, simulates them, and we want to use them to forecast the wildfire intensity for GFAS, as explained. So we made the problem a little bit smaller because we started from the forecast for 1 day, 24 hours, based on the previous 24 hours. We use as an input for the forecast the fire from the previous day, but want to predict the fire for the next day. But we also use as an input the meteorological parameters from the previous day and the forecast of the meteorological parameters. And then we want to train the model with it and want to predict the fire. And the projection should be better than systems, because that's the kind of approach. That's what we're going to do. So in principle, it looks like this, that we use the animation would not work right. But so we have in green, you see the IFS, which is the integrated forecast from the ECMWF, which concludes the meteorological parameter for the past 24 hours and the next 24 hours. And we have GFAS with the past 24 hours of fire-related power, which we feed into the model. And then we have the prediction, which produces the next 24 hours and is compared with the GFAS data for the next 24 hours. And that's the method how we train the model to predict wildfires. So how do we select the meteorological parameters? We looked at the correlation of some parameters from the data set, and we choose actually 5 parameter variables. Small typo. We choose the volumetric soil water layer in the upper layer, the 10-meter absolute wind velocity, the skin surface temperature, fire rate of power, and the uncertainty of the fire rate of power. Why do we choose them? You can see here in the plot the correlation for some parameters. Those are more than are listed here because we have relative humidity, volumetric soil water layer, and total precipitation rate. And the plot you can see here that volumetric soil water layer 1 has the highest correlation and kind of captures the physical relation between water and fire. So as the first step for the training, to make the problem a little bit simpler, we choose the volumetric soil water layer because from this information we assume that has the most influence, and we want to use physical parameters so that our model does not learn to tries to predict the fire from maybe some correlation in the structure of the data or some arbitrary parameters that might be correlated, but from the physical parameters. For the area, we choose the latitude band between 30 and 70 degrees latitude, so that we have North America and also Europe and Northern Asia. And for the time period, we have the periods from 2020 to 2022, from May to October, and from this year from May to June for the training. This is the case. We also applied our model to from data from this year from wildfires from July to August in Greece and Canada. An example. For the resolution, we have a resolution of 0.5 times 0.5 degrees and a temporal resolution, which is hourly. The training for one model took around 30 minutes on an NVIDIA A100, which was supplied by resources from the ECMWF. But because we used hyperparameter training to find the best parameters for a network experience plot, of course, the total training time to find a good model is larger, but for a single model, it takes 30 minutes. And the prediction is quite fast for one day. Yeah, there was some animation. You can see the relics of that here. Yeah, we tested the current approach with persistence as a baseline, of course, because that's what we want to be. But we thought also about let's not just dive into neural networks, but test some simpler models. Maybe let's see, maybe we don't need neural networks. Maybe it works well already with the linear regression or regression tree. Just a basic concept. Linear regression is just a linear model. I'm swapping out the screen. And the regression tree is conceptually you divide the input space and then look for events that are similar to predict them with what you have in the training set. So it's in this case not important, but those are simpler models that don't have quite the complexity of a neural network, so they're not as flexible fit to the data. And then we use neural networks. We actually use an ensemble of 5 identical neural networks. The idea behind that was that we have a easy way to get uncertainty prediction for our results because we use an ensemble and we can use a standard prediction. So let's look at the results of all 4 methods. So on the left side, you see a table with the results. We have 3 metrics in total. So we have the mean average error, the root mean squared error, and the correlation. In the first line, we have the persistence, which gives the baseline. And you don't have to look at the exact values from the other 2 models, only check the neural network ensemble. And if you compare each metric, you can see that it improves quite by a lot. The prediction, what would actually be expected, what we hope for. And on the right side, you can see a plot of the fire rated power. So it's again the 48 time steps. So in black, do you see my mouse? Yes. You can see here the measurement, and then the measurement goes down here. So it reduces. And you can see here in red is the neural network, and you can see that it follows the measurement, whereas the spread from the other models is quite huge. So you can also see in a small example that the neural network does something better than the other models. But let's look into detail into 2 small examples. And one has to say for this, it's a neural network. We did not test if it's physically feasible. We just looked at small examples. Maybe this might be a step for the future. We check if it's physically feasible. So here's an example forecast of the neural network ensemble. Again, 48 hours. We have the 24 hours, the past day and the next day. We have in black the measurements with the uncertainty of the measurements. And in red, we have the prediction of the neural network ensemble with in lighter shaded red, the standard deviation of the ensemble. And we have 3 more variables. We have the volumetric soil water layer in green, in dotted green. We have the temperature in blue and the wind in gray. And one can see here, first, there's a diurnal cycle of the temperature. So you can see here it's the afternoon peak of the temperature and the lowest point in the night. And one can see here that the volumetric soil water layer goes down during the 48 hours, and the wind somewhat varies and goes up towards the end. One can see that the fire on the second day is slightly larger, but the ensemble of neural networks doesn't really capture it, but it shows the same diurnal cycle. So we see here that it's very low, which is during the night, and then increases again during the day, but not as strong. And another example here, again, same colors, but different measurements. So we have here again the measurements in black. It goes up and then goes down during the next day. And one can see here that the volumetric soil water layer has a steep increase here, and also there's a temperature drop. So one can safely assume that it rained at this time step. And one can see that the measurement goes down and the neural network ensemble as well. So that might be a hint that it picks up on the physical reality of fire. But to say if there's a causation has to be followed. It's just a look at correlation to understand why it's better than persistence. And we also look at longer time series. So this is for Canada. We looked at a fire pixel here from this year, from July to August. And again, in black, we have the measurements, and in red, the prediction. So now it's just for each day, that's one prediction. And one can see here first that the fire rate of power compared to other figures is very large, because this is like very large fire. And the ensemble does not really capture the magnitude of the fire, which is kind of expected because this is a very large fire, and the training set there were not as much large fires like this. So of course the model will be closer to the mean values of the fires. But there's some other things as well you can see here. First, to the size of the fire, you see that it does not go to 0 during the night, and the model captures up. So you see here that it follows the curve of the measurements. And another thing that it does quite well in Spot is that it can predict the end of fire. So we trained not on to predict when a fire is starting, because it's highly random and depends on a lot of factors, but we started with if there's a fire, how will it develop? And you can see here, especially in this one, that it really predicts that the fire goes down at this point. So for future research might be interesting to look at like the exact factors that causes this, but one can already see in the Spot that the algorithm can predict if the fire goes out, which Johannes mentioned. There will not be a false alarm, because in the forecast, we have the prediction that the fire will go out. We have another example from Greece, which is similar. We see here that the prediction is a little lower, or quite lower than the actual fire, but it also captures that it does not go out during the night, and that it stops at the right time. So we all documented it on GitHub repo with a lot of README files. Hopefully make it clear what we did, and that it can be replicated, how we trained our models, tested our models, and how you can implement them yourself and get the data. You can find it on the ECMWF Code for Earth site under Fire Forecast. And to summarize, we developed a framework to train and test machine learning models for wildfire forecasting. So in principle, you can add your own model and compare it with the other models. And we also trained an ensemble of neural networks, which produces more accurate forecasts than the current persistence approach. And all steps are documented on GitHub and should be able to reproduce them. We also have an outlook, what can be done in the future. The model can be expanded to include more variables in the training, maybe also increase the size of the data set with data augmentation or some other methods. And the model can also be integrated in the GFAST-CAMS pipeline to actually use it for forecast. And then if it would be introduced in the pipeline, we saw the plot with the pollution here in Bologna. And we, at the moment, we tested it with the other GFAST data, but we haven't tested or compared it to real measurements. And the ultimate goal would be to see that using the improved forecast would actually improve the forecast of air pollution compared to measurements at real stations. So that would be an update. And again, I want to thank our mentors and also Roberto and Xavier, who helped us with technical stuff with like the servers and and the GPUs, and of course Athena and Esperanza for helping us during the coding phase before and after. Thank you very much.
Yeah, exactly. Thank you, Robert. Stay here. Maybe there are questions. No, don't leave yet. So I'm cornering you. So thanks a lot for this presentation and the insight into the work you did. Are there any questions? And yeah.
Yes. Thank you for the presentation. I'm Luigi from the Atmospheric Composition Dataset Explorer. I wanted to ask you, you mentioned about using an ensemble of neural networks. Can you expand a little bit on like why you used an ensemble and the improvements of using versus using a single neural network with a vector output?
Yes, of course, it's a good question. If you just use a single network, we just have like one forecast for the time. And the idea behind using ensemble was to have some spread of uncertainty. There are other methods as well to achieve this, like for example, one could try to predict also the uncertainty with one neural network or use some other methods. And we choose the one that we train in ensemble. And we saw that it performed better than just one. And yeah, so we choose the ensemble in this case to have kind of uncertainty.
Thank you. And I have another question. Nobody else does.
Yeah, we have when we have a question online as well.
Oh, okay. Just a very quick one. Like the regression trees algorithms, which one did you test?
Which regression tree?
Yeah, like did you use XGBoost, StatBoost, or like random forest, or just like basic decision tree?
Just a basic tree. We did not focus too much on the simple models. We
Okay.
just want to see like if they work right off the box, but we did no like hyperparameter search or try to improve the models as much.
Okay.
As we did. So it was just a baseline test with no hyperparameter search.
Thank you very much.
I put for the online, there's online questions later. When predicted the fire, is this based on the observation or are the meteorological parameters controlling this?
That is a good question. We don't know. I mean, we feed the meteorological parameters into the model and also the fire. So in principle, it shape of the fire, it could say that this causes the model to predict that it goes out. Or if there's some event in the meteorological parameters. I mean, this would be a task for methods of explainable AI to find out, because at the moment I don't feel confident to say what it calls, but maybe you need to say something.
I think you have to be aware that it's not based on the observations of the fire going out. That's the point is it's not based on the observations during the second 24-hour period. So it's based on the fire observations previously while the fire is still burning, but then the prediction of the fire extinguishing or increasing or decreasing is based on the meteorological forecast. So in that sense, at the time of the change of the fire, that's only based on the meteorology and not on the observations. And only so it's because the fire observations only come in from the past. So that sense, I think that was really the task to forecast this without having the observations how the fire behaves.
Thank you. There's
Hi, I'm Jonathan from the Diffusion Model Project. I was wondering about the test set size of it. So this is only 2 years. Like, is there a reason why it's so small? And do you think it's a limiting factor of the method?
I mean, it's 2.5.
Yeah.
But so, it's 3. That's
Okay, but it's not like 30.
So yeah, I mean, it's hard to say because we did no experiments with increasing training set size or decreasing training set size to see how the model changes.
Yeah.
I mean, that would be definitely a question for the future. But if we choose a distribution of, I think, 80% of the slides I think here 80% training, 10% validation, 10% test.
Yeah.
So that gives you approximate size. But initially we thought about using only Europe for the wildfire forecasting, but we extended the period to the northern latitude band to have more samples. Behind that.
Okay, so the observations only start in 20 something, or what is the reason that is there only no data set available earlier than this time, or?
I think it was a technical
Okay.
choice.
Yeah.
Because we thought it worked already then, and we did not increase the training size further. Yeah,
Okay.
it would be a good experiment to test it.
Thanks for the answer.
Other questions? Good, then let's have a round of applause for Olga.
And thank you very much for the questions.
Yeah, now we have one participant that unfortunately couldn't make it to Bologna today. So Laura Mack recorded her presentation, so we will see the recording. And afterwards, her mentors who are also not here today, but they will introduce her online to the general audience. And that, oh yeah, topic, benchmarking surface heat fluxes. And yeah, as said, it's pre-recorded, but again,
okay. Hello, everyone.
And we can also take questions.
In this presentation, I want to present the results of our project on benchmarking surface heat fluxes. And I work together with Jasper, David, and Christoph. So the general aim of our project was to develop a tool for benchmarking land surface modules of ECMWF models. And why is it important? Because the surface heat fluxes are a very important part of the surface energy balance, and they determine the exchange processes between atmosphere and surface. And there are two types of turbulent heat fluxes. That's the sensible heat flux, which is driven by temperature gradients between atmosphere and surface, and the latent heat flux, which is driven by moisture gradients between atmosphere and surface. And they depend on, for example, orography or vegetation and the moisture availability, also on incoming solar radiation, for example. And in the bottom right plot, you can see exemplarily the seasonal cycle of sensible and latent heat fluxes. And you see that during the summer month, we have positive fluxes, and during the winter month, they are close to zero or also slightly negative. And this means in terms of the sensible heat flux, we have a positive sensible heat flux when we have unstable stratification, and a negative sensible heat flux in stable stratification. And for latent heat flux, the latent heat flux is positive if we have evaporation or transpiration from plants, and negative latent heat flux indicates condensation or deposition. And the status quo was that there's this Python package Landwehr, which allows for validating soil temperature and soil moisture. And we wanted to extend this for the surface heat fluxes. And for this, we use model data and observational data. And for the models, we consider three different kinds. So first of all, ERA5, which is one online, fully coupled with data assimilation and has the resolution of about 31 kilometers and 1 hour. And then ERA5 land, which is one offline driven by ERA5 with a higher resolution, 9 kilometers, and temporally 1 hour as well. And then we use additionally the hydrological forecasting system, which is also one offline and driven by ERA5, but contains an updated vegetation scheme and has a resolution of 31 kilometers, but temporally just 6 hours. And we compare this with eddy covariance measurements. That's the classical type of measurements for turbulent fluxes. And as you can see in the figure, this is a sonic anemometer, measures wind speed in a very high frequency, for example, 20 Hertz. And this is combined then with thermometer and hygrometer measurements, so for temperature and water vapor mixing ratio, which measure as well in a very high frequency. And the portal which provides such measurements is the Integrated Carbon Observation System, ICOS. And this contains all the flux towers in Europe. And these are really point measurements. And they, in the end, are averaged over 30 minutes. Yeah, so we want to compare the model data with the observational data. And for this, we need to do some pre-processing. So first of all, you can see in the figure on the right side, all the ICOS stations in Europe. And for every station, we find the closest model grid point. And then we do some adaptations. So we convert units, adapt the sign convention and the time resolution, and convert the time zones. And important is also that the fluxes are instantaneous measurements, whereas the model data is normally accumulated, so it has to be deaccumulated. And then we apply some simple quality control to find very negative or unreasonable high fluxes. And we also delete incomplete time series. And then we have a time series for the model and the observation. And in our case, we just consider 2020. And for this, we can then apply several validation metrics like the correlation coefficient or the bias, for example. Okay, so I want to show some of the results, exemplarily for ERA5. And first of all, you can see here the diurnal and seasonal cycle of the sensible heat flux. So the left plot shows the model and the right plot the observations, averaged over all stations. And on the x-axis, you can see the month, and on the y-axis, the hour of the day. And we see that the diurnal and seasonal cycle coincide very well. We see these high values during summer and day, and the negative values during nighttime and winter. But we also see that there's a quite big difference in the amplitude. And to investigate this a bit more, we can look at just the diurnal cycle. Here again for the sensible heat flux. You can now see on the x-axis the hour of the day, and in the left plot the linear correlation averaged over all stations again. And we see that during daytime, we have a very high linear correlation of 0.8, whereas during night and especially in early morning, we have a really low linear correlation of just about 0.3. Whereas if you look at the bias on the white plot, we see that the bias is very negative during daytime, so up to -60 watt per square meter, and slightly positive during night, so 6 or 7 watt per square meter. So this, we can summarize that during daytime, that the model is quite good in predicting the diurnal cycle, but also because the fluxes are quite high during daytime, there's a quite big difference. So it's easier to have a big difference if the fluxes are already big. And during night, we have a very low correlation, so the model does not add any on just the bit scale to the diurnal cycle. And the bias is quite low because the fluxes are already low. But here the bias is positive, which means that the model slightly overestimates compared to the eddy covariance measurements. Yeah, so we saw that there's a strong diurnal variability. So we can also look at the daily average of the fluxes. So here you can see, again, the linear correlation and the bias for sensible heat flux. And now you can see on the x-axis the location of the station, so their latitude. And you can see that for the daily average values, we have on average very high linear correlation of about 0.8. Even if it's during nighttime, we just have a very low linear correlation. just some stations, especially for the southern stations, and latent heat flux sometimes has lower correlations. And if we look at the bias on the right side, we see that the sensible heat flux has on average a negative bias, about -20 watt per square meters, and the latent heat flux on average, there the bias is close to 0, but we also see a slight latitude dependence from negative values at the southern station to more positive bias at the northern more stations. So this, we can summarize that the sensible heat flux is overestimated, but the latent heat flux there we see especially a latitude dependence. Okay, then I also want to look at the flux partitioning. So flux partitioning means to look at the ratio between sensible and latent heat flux. This ratio is sometimes called Bowen ratio, and this is an important dimensionless quantity to describe the climate. So for example, we have a high Bowen ratio if we have more sensible than latent heat flux, which indicates a drier climate, whereas the Bowen ratio is lower if the latent heat flux is larger than the sensible heat flux, indicating a more wet climate. And here you can see on the left plot the seasonal cycle now, the month on the x-axis, and then the sensible and latent heat flux for the OPS and the model. So you can see that the sensible heat flux for the OPS is much larger than for the model, whereas for the latent heat flux, there are just smaller differences. And if we now look at the ratio on the right side, we see that the OPS has for every month a higher Bowen ratio than the model. And the difference is especially dominant during spring and summer. And this shows that the model has a lower Bowen ratio on average, which indicates a more wet climate. Okay, to summarize this first part, we looked at the diurnal and seasonal cycle, and we saw that during day and summer we have a very high correlation, but also high negative bias. So on average, the model underestimates the fluxes. So an example for this is that during convective boundary layers, there are very large eddies, and often their heat transport is underestimated by the model. Whereas during night and winter, we have a low correlation and a slightly positive bias. So the model tends to overestimate the fluxes. And this low correlation, that's a special issue in stable boundary layers. And this is because the turbulence in stable boundary layers is very weak. So it's not a well-developed turbulence. So the turbulence is very intermittent then, and this is really difficult to model. Yeah, we also saw that if we look at the daily average, then we get a high correlation between model and OPS. And this additionally indicates that there's a strong dependence on the averaging or accumulation times, which should be considered for the interpretation of the validation of the fluxes. And we looked at the flux partitioning, and there we saw that the ratio of sensible to latent heat flux in the model is lower, which indicates a wetter climate. And now it would be nice to generalize this and have a package that does the validation automatically. And for this, we use Landwehr. And as already mentioned at the beginning, it was developed for soil temperature and soil moisture, and we extended this now for surface heat fluxes. And the idea is that you really call just from the terminal Landwehr and then a name list. And the name list specifies the parameters. So for example, the used data, the control experiment and the experiment itself, then the time and the resolution, and they are passed through the class. So that's the core of Landwehr, the class LDAS, for land data assimilation. And this name list parameters are attributes in this class, and there are additionally some other attributes. And this class also has several methods. So I just mentioned here the three important ones. So the pre-processed data method, as the name indicates, is for the pre-processing of the model data. And then the method in situ validation is performs the validation of the model versus the in situ measurements and applies all the metrics. And then there's also this method web create, which creates the output. So it summarizes all plots and tables in an HTML file. And this HTML file is the output of Landwehr. And here's an example of this. So you can see that that's summarized in several tables. And you can see, for example, the command which you use to call the validation. Then there's a summary of the used experiments, for example, here ERA5 and the hydrological forecasting system. And then the summary of the validation metric starts. And here, for example, you see map plots. So then we have one column for sensible heat flux and one for latent heat flux. And here we look just at Europe and have then for both models separately, the correlation coefficient and then a comparison. And then we have also part on box plots indicating if the experiment performs better or worse than the control. And this is done by using this Fisher-Debt transformation, which then allows to say if there's a significant improvement of the experiment versus the control. And then there's also part summarizing all the scores and tables. So for the annual score and then for the seasonal scores. And this is separated for every network. Here we just use ICOS. And then there are also more metrics and also some other plots. And here's our examples of these plots. So for example, here the left plot is the map plot. You see Europe and then the station location color-coded depending on the correlation coefficient. Then you can see here bar plots indicating the significant improvement or if the experiment improved the control or not. And then here's a table summarizing several scores. So you can see this here for our year 2020, and 33 stations were used in the validation, so they had good enough data quality. And normally we do the validation for several years, and then you would see every year separately, and then the period is summarizing them. But here we use just 1 year, so they are the same. And then you see here in the upper right plot, the bias based on the season. So there we see this well-known pattern already. And so you can also see how many stations have been used per season. And there we can also see that during winter and autumn, less stations have been used, which is because of, most of the time, worse data quality of the eddy covariance station during winter. And then you can here see also an example for such a time series plot, which helps to indicate if there's a good alignment of the seasonal cycle, for example. And with this, I want to summarize the second part. So we adapted the Landwehr package for surface heat fluxes, and mainly we did we adapted the pre-processing of the fluxes and added some new nameless parameters for the time conversion, and also the plots and the HTML output has been adapted. And we did some example validations for the hydrological forecasting system versus ERA5, and also for ERA5 land versus ERA5. With this, thank you. And also thanks for the organization and also the opportunity to do a pre-recording, because unfortunately I couldn't attend. Thank you.
Yes, as I mentioned before, Laura she also couldn't be online, but we have her mentors online, and we gave, hey David, hey Christoph. Maybe you can introduce Laura in a few words, and then we can also take questions afterwards. Again, for the audience participating online, please use Slido. We here in the room, we have a microphone. So Christoph, I think you it's
Yes, can you hear me well?
loud and clear.
Perfect. Yeah, good morning from my side to Bologna and all of you. My name is Christoph, and so I was proposing the challenge with Jasper Danielsen from the coupled process team, and David Fairbairn, who is also online now, and myself from the coupled assimilation team. Yeah, we're proposing the challenge benchmarking of surface heat fluxes, because as you know, the weather forecast is not only done in isolation in the atmosphere, but we're also running sort of coupled models. And to get the coupling between land and atmosphere right, yeah, it is essential to accurately estimate the heat and surface, or heat and moisture exchange at the surface. And here comes into play basically what Laura just said in the surface heat fluxes, which have usually a strong diurnal cycle, and is essential in order to get these fluxes right in our model to calibrate and validate them. And this is done with this in situ data. Here, and a couple of years ago, David developed at ECMWF the land verification package called LandVer. And at the moment, it was only used for soil temperature and soil moisture verification at the surface and the root zone. So our let's say 3 main objectives in the challenge were basically adding surface heat fluxes from the ICON station network into the LandVer package, and also being like testing to validate analysis experiments. Here we have it like results of our models as ECMWF and looking at the diurnal cycle. Yeah, and what Stein also mentioned here, it's we're going towards open source. And I think making LandVer available open source is very beneficial to ECMWF and also the scientific community when it comes to validation of surface fluxes. And yeah, so we were very happy that Laura wrote us a proposal. So she's a PhD student at the University of Oslo and working on stochastic parameterization of stable boundary layers. And she has a good background, a practical experience working with eddy covariance stations. And yeah, it's been a pleasure to having worked with Laura. Yeah, she successfully added data to the package and yeah, mastered basically all the challenges which were involved. So very beneficial for us. And yeah, it's a pity that she couldn't make it to Bologna, but yeah, David and me, we are here now to take questions. So yeah, go ahead if you have some. Thank you very much.
Thank you, Christoph. Are there any questions?
Hello, I'm Mohit from the diffusion challenge on the weather bench. I just had a question where in one of the plots we did see that the correlation between the fluxes were much worse during the nighttime compared to the daytime. Do you have any idea why it could be? Because on the other hand, we see the biases are more during the daytime.
Yeah. So yeah, David, do you want to go or sorry?
I don't mind. I mean, I think yeah, I think it's because during the nighttime the absolute values are much lower. So it's basically it's the correlations are lower. Just I think because you've got very, very small fluctuations, and that's sort of getting towards the kind of limit to what the measurements can accurately and the model can accurately predict. So I think it's just because of the absolute values being a lot lower at night, which is why the correlations are worse. That's what I understood.
Yeah. Okay,
Yeah.
thank you.
Yeah, it sort of can also run into the noise level already somehow.
Yeah.
And then correlations are usually lower.
Any other questions from here in the room? On Slido? No. Good. Yeah, then well, that's the end of the first session before the first coffee break. Thanks again for Christoph and David for joining online. And yeah, an applause again, and we can give it to Laura. For the people on yeah, so for the people online, we will have a half-hour break. We will resume at 11:15 CET. And for the people in the room, we will go downstairs to the patio. Follow Esperanza, she's our leader. And then also please be back 10 minutes after 11 so that we can continue at 15 past. Yeah, we will either someone will be here or we will lock the room. So definitely.
just don't mean nobody no good, believe me. Should have been called devil's dust instead of. Believe me, children, ain't trying to run your life, but that was when he could have sworn the room was moving. But that was only in his mind. He was sailing. He never really seemed to notice a vision failing. Cause that was all part of the high. The sweat was pouring. He couldn't take it. The room was exploding. He might not make it. Please, children, would you listen? Just ain't where it's at. You won't remember what you're missing, but down some dead end streets there ain't no turning back. They were standing, everybody in a circle, the whole family. I listened to the preacher's words, sis was crying. She alone held the secrets about his dying. Tears falling to earth, the baby heard fall. He was so trusting, God only knew why. They were dusting. Just ain't where it's at. You won't remember what you're missing, but down some dead end streets there ain't no turning back to back to back to back from. Take it. The room was exploding. You might not make it. Please, children, it's hard to listen, but I ain't trying to run your life. Might just seem like one more good time, but down some dead end streets there ain't no turning back.
Maltratei, sim, maltratei demais. E machuquei, meu coração que bate calado, 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 que bate, bate. Oi, 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 oi. maltratei, sim, maltratei demais. Me machuquei, que meu coração que bate calado, 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 que bate, bate. Oi, 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 oi. Que bate calado, 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 que bate
You sang the marquee here, very end you knew the cost. It was a temporary fix. You sang the marquee here, very end you knew the cost. It was a temporary fix.
Spirit desire, face me, don't displace me. We will fall, miss me, don't dismiss me. Spirit desire, spirit desire, spirit desire, spirit desire. We will fall, spirit desire. Spirit desire, spirit desire.
All you've got is this moment. 21st century's yesterday. You can care all you want. Everybody does, yeah, it's okay. I need you tonight, 'cause I'm not sleeping. There's something about you, girl, that makes me sweat. So slide away and give me a moment. The moves are so raw. I've got to let you know. I've got to let you know. You're one of my kind. So slide let you know. You're one of my kind. How do you feel? What do you think? What you gonna do? So slide over here and give me a moment. Your moves are so raw. I've got to let you know. I've got to let you know. You're one of my kind. Until tonight, 'cause I'm not sleeping. There's something about you, girl, that makes me sweat. So how do you feel? I'm lonely. What do you think? Can't think it out. What you gonna do? Gonna live my life. How do you feel? I'm lonely. So how do you feel? I'm lonely. What do you think?
tutyoborwa lwaki tulengezwa.
grand-chose dans la vie. On va boire trop. On fait la fête de semaine. On va faire la fête de l'année. On va faire la fête de millénium. Tout le monde vient ici. Mon ami, il faut que tu fasses doucement, tranquille, faire doucement. Ça marche, ça bouge. On a dansé. On a bu. Mais ça va. Il a déjà beaucoup soirée. On va faire la fête.
Right. So we put on the AC, it will get colder again. So less warm depending on your perspective. Here I'm ready.
Yes, you're ready.
Can I speak? Okay, welcome back everyone, and it's also nice to see that the group here in Bologna grew. So we have more people coming. That's nice. We are at the second part of the morning, the second session at the final day event for Code for Earth. Welcome also the audience online. And I keep it very short. We have now three presentations. The first will be diffusion models on Weatherbench with Moid Anand and Jonathan Weider. And you will introduce Jesper Drams will introduce the presenters, and then we'll have two presentations on regional reanalysis, and that's a Spanish team, the deep reanalysis with Antonio Perez and Mario Santa Cruz. And Mariana, she is the mentor, she will introduce them. And the Tesseract team is Irene Schicker, Sebastian Lehner, and Konrad Meyer. And again, Mariana will introduce. So, but first, diffusion models of weatherbench before this.
Hello, I was the mentor of this nice project, and I want to give a little bit of context for this because diffusion models are fairly new, and like weatherbench is also like relatively new, but I want to keep it short. So these two have been working really hard on basically getting a very new idea in deep learning. So just So yeah, diffusion models are a very new idea in deep learning. You'll hear more about that. And the idea that we can actually forecast the weather with machine learning accurately is about a year old. So I figured I'd victimize two other people to try out this new method on this topic. And diffusion models are really cool because you can also do ensembles with them. And in every meeting I have with like DeepMind and NVIDIA and all these big companies, they have essentially two topics they want to talk about, and one of them is ensemble. So with that, I give the stage.
Hello, everyone. I'm Mohit, and I'll be presenting together with Jonathan about the diffusion models on weatherbench. We would like to thank Jesper, Florian, and Matt who helped us throughout the entire project. We would also like to thank Athena and Esperanza for taking care of all the organizational details. And yeah, so I'll start with the diffusion models. So in last 6 months or so, we have seen many examples of diffusion model in the form of stable diffusion or DALI, where we have some conditioning information. It could be in the form of text or images, and then we again generate images. For an example, this conditioning information could be something like this: a cute image that I can use to illustrate a presentation on machine learning for weather predictions. And then you get cute images like this. But we are not just interested in the cute images. So in our midterm, we explained the diffusion models in detail. And here we will just give a very high level overview. So a diffusion model takes some noise as an input together with some conditioning information. For example, in our case, it's the current weather, and it helps us produce some predictions in the future time steps. We are using weatherbench dataset to train our diffusion models. Weatherbench dataset include ERA5D analysis dataset that we already saw in the introduction lecture as well. And we are using two relatively coarser resolutions, which combines of 32x64 and 64x128 pixels. The time steps that we are using is the temporal resolution of the dataset that we are using is 6 hours. And generally, in most of the cases, we use previous 3 time steps of data to predict the future. And for our case, the training set consisted of the data from the year 1979 to 2015. The validation set was for the year 2016, and the test set was for the year 2017 and 2018. The data set consists of many different variables like geopotential height, temperature, humidity, and wind at multiple pressure levels. We select a subsample of them. And since we have multiple variables at multiple pressure levels, the data set quickly becomes quite large. And it took roughly like from 12 hours to 1 day to train each of our model on 800 GPUs, depending upon the complexity of the model. Today, we have our diffusion models in 2 settings. One is iterative, in the setting of iterative prediction, and the second one is direct prediction. In iterative predictions, we feed an input at a time step and then predict the next time steps based on the output of the previous time steps. While in the direct prediction, we start from a time step and directly predict the time step we are interested in. Both the methods, iterative prediction and direct predictions, has their own advantages and disadvantages. For example, when we do an iterative prediction, we get the evolution of the dynamics throughout the entire time, while when we do the direct prediction, we reduce the chances of errors accumulating from one model to the other model. The other thing about iterative prediction is we also need to produce at each time steps all the input variables for the next time steps. So I'll quickly go into the results. So what you see on the leftmost panel is the target, which is geopotential at 500 hectopascal. And what you see in the middle panel is the predictions with an increasing lead time. And the rightmost panel shows the difference between the target and the prediction. What we very clearly see that our error or the difference between the two is increasing with lead time. At the same time, the errors are larger in the high latitudes compared to the middle latitudes. But this is just one specific variable. So we did this again for the temperature at 850 hectopascals. Here also we see that the difference between the target and the prediction keeps on increasing with time. Though the errors are larger again on the higher latitudes, the difference between the errors between mid and the higher latitudes is less compared to the geopotential at 500 hectopascals. So now we have seen that we have this qualitative results or good images, but we need to do more quantitative analysis or compared with different baselines. For this, the first wave of deep learning methods for weather prediction came with the weather bench, with the release of the weather bench data sets, and we had different models starting maybe say roughly around 4 to 5 years back. And now, as Jesper already mentioned, like there are many different models coming up from the industry. And some of them, like each of them uses a different kind of network, like adaptive Fourier neural operators or vision transformers or the graph networks. But what we don't see there is the diffusion model. And one of the aim of this project was to really explore diffusion models to do, to see how well they do compared to the different models. And we also see that for most of these models which came up in last 6 months or a year, they competed quite well with the numerical weather predictions, even outperforming them in some of the metrics. And thus, yeah, the idea was to know where does the diffusion model stands in general or how well does it do. And from here, maybe Jonathan will tell you more about the results.
Thanks. So I have to start with a slightly disappointing message. So we were not quite able to keep up with Google and NVIDIA. And so we show in this plot, we will show like roughly the performance that we had. And what we plot here is actually like the root mean squared error. And we plot this like for averaged over the entire globe, weighted by area. And we plot this as a function of the lead time. So how many days we want to predict into the future. And what we show this is the root mean squared error for the geopotential height, which like in case somebody doesn't know, it is just like a standard meteorological variable and tells something about like pressure systems, for example. Okay. So what everybody's trying to beat is the ECMWF's operational model. And this is this dotted line here. So the best entry in WeatherBench was before this NVIDIA era, was still quite a bit worse than this. And it turns out like our diffusion model, at least with our implementation, is still a bit worse than this. But on the WeatherBench data set, we are somewhere in the middle. So we're beating a lot of the baselines they have. We're also beating some of the machine learning models, but we are not competitive with the very best model. So the question is then, like, why would you even want to use diffusion models? Are there reasons you would even use diffusion models if the overall performance in terms of root mean squared error is a bit worse than for other models? And as Jesper already said, one thing that's really cool about diffusion models is that you can create ensembles. You can do this the following way. So if you remember the introductory example by Mohit, we had like one conditioning information, and then we created like a bunch of images. And we can do the same thing here. So we can start with one initial weather time step, and then we can create like a bunch of different possible realizations in the future. So for example, we could predict 3 days ahead in time, and then have a bunch of ensemble members, and then we can have a nice probabilistic analysis. And so it's also somewhat related to the talk we had earlier on like the fire forecasting. We also created ensemble members. Okay, so before I show some results, I think it's worth like selling what actually like what are we aiming for. So what is a good ensemble and what is like a good ensemble spread? So conceptually, let's imagine it like this. Let's say, okay, we choose randomly some pixel and we choose a random value, for example, geopotential, and we start at a given time point, and then we do a prediction, and we end up with like a bunch of realizations from the ensemble predictions. And this ensemble then has a spread that might be like the standard deviation that I call sigma here. And then let's assume we have a true observed value that lies here. I think in this case, like most of you would agree with me that the ensemble is like a bit too narrow because like the true value is even outside the range of all the ensemble members. But what we also don't want is like the opposite. So it would also not be great if every two observations would lie perfectly in the center and the spread would be very large, because then, of course, the ensemble could just decrease its spread and we would have more precise information. So actually, there's a sweet spot between these two, and this is precisely the case when this root mean squared error between the ensemble members and the true value equals the spread of the ensemble. And this is exactly the metric that we will use in the following slide. So let's go step by step. The first thing that we computed is the root mean squared error between the true value and the ensemble members. In this case, it's an ensemble with 5 members, so it's just a very small conceptual example. And we can see that this also confirms with what Moritz showed earlier, that the errors grow the largest over high latitudes, and we can see that the root mean squared error is also largest in these regions. So now the ensemble standard deviation also follows this trend. So in general, the ensemble spread is largest in the region where also root mean squared error is largest. But as you can see, the colors are quite a bit fainter here, which means that the overall values are also smaller. And to quantify this, you can take like the ratio of the two of them and just divide root mean squared error by the standard deviation. And if you remember from the last slide, this ratio, so these two things should be equal, which means that the ratio should be 1. So ideally, this map would lay somewhere close to 1, but actually what we observed is that we are somewhere between 1.5 and maybe like 3.5. So the overall conclusion that we can take from this is that, yes, we get an ensemble spread, but at least in our case, the ensemble is like not spread out enough, or the prediction didn't work good enough, which is kind of like an analysis. Okay, we also tested this ensemble aspect in a case study. And what we looked into here is like a heat wave that happened in 2018, so in a test set of our data set. And it was a heat wave in Scandinavia that took place from somewhat mid-July until the beginning of August. And yeah, we focus on the region that we highlight here in red, and the values that I will show later are just like average values over this region. And we focus only on the temperatures around noon. And yeah, but shown is just the temperature anomaly. So red means that it's hotter than like in the usual, like in this usual day of year. Okay, so if you have a heat wave, it could be nice to be able to predict this ahead. So as an experiment, we went to like a very large prediction lead time. In our case, this would be something like 5 days. And then we would start from, for example, for this point here, we would create a prediction from the 5th of July. And then you can, we would, for example, get this realization of the machine learning model. And you can see, okay, there's quite some error between the machine learning model and what actually happens. And then you can continue with this process and do this like for every time step in the model. And as you can see, so the nice thing about diffusion models is that they don't only get a single realization, so you get like a spread. And what I show you is just like all the ensemble members and taking the minimum and taking the maximum of the ensembles. And yeah, if I go through this to the end of the heat wave, you can see, first of all, this doesn't quite match. So at least for the very long lead time that we chose, our model didn't manage to predict the heat wave nicely. But overall, we can see that the rough shape is somewhat represented. And I think we can still convince you that like having this ensemble spread is better than not having the ensemble spread. All right, and then like a third analysis that is something that might turn out like emphasize the value of diffusion models is the fact that many of the machine learning models, they tend to produce very smooth predictions. And so I think I want to give credit to Mariana here, who shared the code to produce this figure. And so what we are going to plot here is basically a spectral variance, which says like how much variation is there on a specific scale. And on the bottom, we have the wave number, and this ranges from like large scale structures on the left to very small scale structures on the right. Okay, and this is what we actually get. So what you see here is in black, what is actually the observations. We see in green what our dashed green, what our ensemble does. And in blue, we have one baseline. This is typically used in like image analysis. So it's a UNet model. I think like if you do like computational like machine learning, you've probably heard of this model before. And so I also have to say that the UNet here was better in overall predictions than our diffusion model, but you can still see like in this metric, it's not quite as good. You can especially see this in this region here. So you can see the UNet curve is quite a bit lower than the diffusion model curve and also the target curve. And this means that there's too little variability in this frequency range. And this basically means that there's like these structures are smoothed out too much. So we can see that at least in this aspect, diffusion model really paid off, like using it paid off. Okay, then I think I can already come to the conclusions. So what we did was largely exploratory work. So nobody had tried this diffusion models ever before. And it's also, you have to keep in mind that we're competing with like people like Google and NVIDIA on this topic. And yeah, so the main challenges that we faced were just like the large dataset amounts. And if you have this diffusion models, there's just a super large design space. It already starts with the variable choices you make in the beginning, because Error 5 has a lot of variables and you have to decide which ones do I take, which ones do I leave out. You can implement a diffusion model in like 10 different ways, and then there's modifications you can make, and just making the right choices in this design choices in this design space is not easy. So to summarize the results, in terms of just mean squared error, our results are not quite competitive with the large deep learning models, but I think people who are interested in this topic further, they might still look into this because of the nice aspects that the method has, which is like the non-smoothing nature and the ensemble uncertainty that we get from it. Yeah, I forgot to mention our code is of course available on GitHub, and if you want to play around with this, try it out, have a go. Yeah. One way to improve the results even further might be including latent diffusion, which is also what these online image generators use. It's just one step more complicated, and we didn't manage to implement this in time. But we did talk with an author of a paper that implemented diffusion models, and he said it's actually something that helps him quite a lot. So I think this is really a promising direction. Yeah, and with this, I want to thank you. And if you have any questions, feel free to ask them or come to us during the day.
Thank you, Mohit and Jonathan. Are there any questions in the audience here? So.
Okay, thanks for the presentation. Very nice work. Congratulations. And actually, it's not a question, it's more like if you, I guess you never worked with diffusion models before this project, or I don't know, but if you have any suggestion on where to start, if someone wants to get some, ideas about it or try to use it for its research.
So I actually had this in an early version of the presentation. I can share it with you later. So it depends on where you want to start. If you want a tutorial to start, there are good resources on this. There also is a good, very good fundamental overview paper that explains like the equations behind the diffusion model.
Okay,
so
great.
So both of them with you.
Okay, next break, I will come to talk with you. Thanks.
Other questions here?
Thank you. Yes, I'm Robert from the Fire Forecast team. I was interested in, it might be difficult to assess, but do you think that you haven't reached the performance of NVIDIA and Google is due to the architecture of diffusion, or is it just because they have more resources, maybe a larger team that has worked on this?
Yeah, so there are different components to this answer. So one of the things that NVIDIA and Google do is that they work on data that has a much higher resolution. And apparently, if you have high resolution data, it's even easier to learn the weather. So this also was one part of that of what actually enabled this breakthrough in the weather modeling, just like going to high resolutions. And this, of course, makes it really hard for people to compete with, because like even at our resolutions, the data is like 2 terabytes. And if you go to like the resolution is like 8 times higher in every dimension, of course, you can imagine what this will like turn out in the end. Also, what you have to put in your GPU.
Okay, thank you.
Yeah, but also, sorry, the second aspect is that there is still room for improvement, I think. So we did compare, like we also implemented a small forecast network. So basically it's the NVIDIA paper that they had, and it was like a bit better than a diffusion model. So I think there's like, it's also a limitation of our implementation to some level.
We don't have any questions on Slido. I still want to remind the audience that is participating online. Put your questions on Slido. Now the applause of
We have one. So they ask, can you tune the diffusion model to have not displayed?
That's actually a good question. So I don't know if there's a trivial way to do it. When you can produce larger ensembles, but you showed were only 5 members. So if you produce 50, you will probably already have a larger spread than the 5. Maybe Jesper can add on this.
Hi. I mean, one simple idea is to use one simple idea is that you not just use the deterministic forecast to use an ensemble, because like the problem we gave them was really hard. If we have like ensemble training data, for example, that should already improve the spread because we have more variable, like fine scale variability in the initial conditions, and then in like some members that go into the extremes, right? So right now, this is just deterministic data that they trained on. I think it should automatically become a bit more tractable if we actually use EDA or something like that. Thanks for the question.
Yeah, so let's go to the thanks again, guys. As mentioned before, we have now 2 presentations on regional reanalysis. And the first is the Austrian team, is that correct? Yeah, so we hear from the project Tesseract, and Irene Schicker, Sebastian Lehner, and Konrad Meyer will present. And my colleague Mariana Klar is here for the team of mentors, and I give you the stage.
Meanwhile, to present to you.
Hi, everyone. So I'm Mariana. I work at ECMWF, and I was the mentor for both this team and, well, one of the mentors for both this team and the next team, along with Cornell, Andras, and Matt, who couldn't be here today, but send their well wishes to both of the teams. So we were really impressed with the work that they did. So the task was downscaling data from ERA 5, which is at 0.25 degrees, to CIRA resolution, which is 6 kilometers, correct? Or 5.5, sorry. And so we originally, there was just one proposal that was sent out, but we had lots of good ideas come through and we couldn't decide between the 2 teams. And so I think Matt spoke to Gina, and so we managed to get 2 teams working on the project, which was really exciting because then we can sort of compare 2 different types of methods. So with that, I introduced the Austrian team, and hopefully your slides will appear. Otherwise, this could be interesting. Okay.
Hey, perfect. Hi to everyone in the room. My name is Konrad. I hope also people online are still with us. Yeah, Mariana also already introduced this challenge, regional reanalysis for Europe, a downscaling project or downscaling challenge. Now we can in the video. Okay. As you see, we are a rather big team for this challenge, and this is why I also brought some other colleagues with me. They're not on the video, but you will see them later on. Irene and Sebastian. They will come in later, but we also had quite some mentors, and you already know Mariana, but we also had some more, so big team, a lot of mentors, obviously. And Mariana already introduced you to the problem we faced. So on the one hand side, we have ERA5, which is a rather coarse resolution data set. And on the left side, you see the resolution we aim for, which is Sarah at 5.5 kilometers spatial resolution. And we have to plug in something in between. We have to find a means or something to get a job done to come from here to there. How was this done? Actually, we were quite ambitious. We didn't do this with only one model, but we aimed to do 3 different things and compare these different models on the go. As you see, we have one baseline model where I will talk a little bit about, which is a statistical model called SAMOS, and we have 2 machine learning approaches where Irene and Sebastian will talk a little bit more about. We have different approaches, but all 3 have something in common, and this is what is indicated by this blue box down here. We're not using the absolute values of surface temperature, but we're rather calculating standardized residuals or standardized anomalies beforehand. And this is done by modeling linear trend and seasonality, removing this climatology, and then getting standardized anomaly, which we use as input data for all the 3 models. So as I said, we used one statistical model as a kind of baseline model, which is called SAMOS. And the idea of these standardized anomalies actually comes from the SAMOS modeling, which is utilizing this technique to remove location specifics beforehand, and especially for temperature, it's also important that we have no elevation specifics included in the data anymore. And we also remove season-specific characteristics by using standardized anomalies, and therefore it's possible to fit one statistical model for the whole research domain. As you see, we didn't aim for all of Europe, but we rather selected one kind of case study region, one start region, which is, can be seen here, which is somewhere in Spain. So after modeling, after applying, for example, this linear model as a reference, we have to add the climatology again to the predicted standardized anomaly you see here. So we apply the climatological spread and the climatological location again to get the final prediction. This is the same for all the 3. So how does the outlook look like in case of SAMOS? You see one specific field here, and on top left you see ERA5, a bilinear interpolation. So you see a rather smooth field here. On top right, you see the target. So this is what we aim for, and below we see the statistical model output for this specific day and time. So you see that we have a lot more small-scale structures in our predicted SAMOS output, but we still have some differences. The previous presentation already gave a good introduction on how to quantify or visualize the degree of how good we are in predicting structures. And to the right here, you see again power spectral analysis, where you have to the right the small-scale structures, and to the left the large-scale structures. So the frequency increases to the right, and the line below is this rather smooth field of bilinear interpolated ERA5. And the two lines above, the dashed line is the SAMOS prediction, and the solid line is the target zero, are pretty close. So we're far better with SAMOS to show small-scale structures than we are with the bilinear interpolation as another baseline. I have to give a shout out to the next team presenting, DeepR, because we're using some of their code for the validation. We chose to do this because then you can compare the figures produced by us and produced by them. We're working on the same problem. And I want to show you just one case here for this validation, a specific location in Spain, in northern Spain, a national park, Picos de Europa, where I pick out one time series. In this time series, you see the red line, which is the bilinear interpolation, in yellow, the SAMOS output, and in the black line, the observation, the zero data. So you don't see a lot from this time series, but you see that the reddish colors are more on top. If we just look at the errors, we see a clearer picture. Where we see we have rather visible bias in the bilinear interpolation, and this bias is removed by this SAMOS downscaling approach. To the right, we see the error distributions, where you clearly see SAMOS is oscillating somewhere around zero, but bilinear interpolation has an obvious bias. So we do a good job in bias correction, but the error is varying to a similar degree than bilinear interpolation. This is also visible if we take a look at the months of the year, so the variation over the year, that we have bias correction which is working all over the year, where the yellow boxes are close to the green observation boxes, but by linear interpolation, actually there's an error, by linear, not by cubic, shows always a little bit higher temperature. The same is the case for all the times of the day. So if we aggregate the predictions for each time of the day, then we're much closer with the SAMOS downscaling to the observations than we have with bilinear interpolation. So if we expand this in space and take a look how this varies in space, we can also see huge differences. The bilinear interpolation shows much higher errors, but to be fair, the color scale is quite big on this plot. So that you don't see any variations here doesn't mean that there are no errors. So I made probably more fair plot here, just showing the SAMOS output. You see the root mean square error here, image here in the center, and see that there are some errors which are also quite high for this downscaling, more than 2 degrees. So in the next step, you can ask, where do they come from? And obviously the errors get higher, the more variation is in the time series. And this variation is also obviously bound to elevation. So probably it would be in the next step good to also add topography as another predictor to our model, but we didn't do this because we wanted to be as simple as possible with this baseline scenario with this SAMOS. Okay, so I hand over to Irene to tell you something about machine learning.
Thank you. Yeah, hello from my side as well. So for the unit, we had quite ambitious ideas to test 2 unit configuration, different configuration of loss functions, and also different configuration of input files. But in principle, the idea was similar to SAMOS. We used the residuals as input, and we had to normalize them. So the residuals are still in a range between roughly -8 to +8 degrees Celsius. So we did normalize the input as well for the unit using set normalized field. And one model is based on the publication of Shah et al. For temperature downscaling and the ECMWF course of last year. in May. And the idea of SHA was to either only have temperature as target or temperature plus the high resolution topography as target field. I'm not jumping ahead, but you will see some issues with the topography as additional target. It has 3 decoder encoder layers. I did play around a bit with the normalization, but in principle, it's not a very deep unit. And the small unit is our own definition, really targeted to the domain we are using here. Can also work with both temperature or temperature plus topography as output. There are differences in the activation functions in the kernel size. What we did for both, because we ran into issues computation-wise and time-wise, we restricted the training period to 2010 to 2016, which will also be one of the reasons why we are not able to beat SAMOS. And yeah, additionally, what is still built in is we could also work with the raw data and not the anomalies. And there are different loss functions possible, but we focused here on the inversely weighted MSE loss to account for outliers. So first results of the unit small, that one used topography as additional target. In principle, you would say it's not that bad, but it's what we see here, and this is a result of the short training period. We have this nasty, in the top left corner, we have this nasty, yeah, let's say residuals, which is some sort of mishap in the filtering. And this pops up at different places during the period we are forecasting and is a result of this short training period. So we need to extend the training period, but we also need to extend the epochs. What we do see in the density is that basically we're not able to beat SAMOS here for this time step. Also looking here into this unit, if we transfer it back and look at Picus Europa, it's basically the climatology, so we have hardly any variation at all with that unit. And this is, if we jump to the SHA-net, this is what we think is related to using the topography as additional target, because we did see quite heavily in the predicted residuals, even before adding back the climatology to the predictions, that we see the topography, and you see it here as well. We see the topography in the predicted residuals, and you don't see them in the SHA, which did not use topography as additional target. So this is one of the reasons why the small unit did not work out as we thought, and why we think that if using residuals is input to something like a unit, not using topography as additional target is advisable. Similar for the error. And if we compare the unit versus the SHA version without topography versus SAMOS, we see that we are not bad with this not perfectly trained unit, but we are still not there where we should be, and we are simply not able to beat SAMOS in this case. And you also see here in the RMSE, you see these nice artifacts in the RMSE plot, which are the result of this short training period. So it's not exactly comparable to SAMOS, and there's still some work to do for the unit. And now I'm handing over to Sebastian and Tegan.
Yeah, hello. Now we have a quick overview of the GAN that we use. So we use the conditional GAN that was developed by Harris et al. In 2022. You can see the architecture on the right-hand side, but I won't go into detail. I'll only mention that the GAN was originally designed for downscaling precipitation, but because we used it as Irene already mentioned, in the form of a purely super resolution problem. We just had to adapt it a little bit, mainly all of the pre-processing pipelines and a little bit about the infrastructure around it, such that we can use it for this purely super resolution problem. The second step is, or the second part is that we had to adapt it for the residuals. So because our input again is only the standardized anomalies, no absolute values. And second, yeah, we have the same as before, only the low resolution temperatures input feature with high resolution orography and the land sea mass. And last but not least, we use the Wasserstand loss for training and optimizing the GANs. So here we have the same example as before. This is just one single day. So if we focus first on the right-hand side, what we can see is that we have a much better performance from the GAN compared to the UNet in terms of the smaller scale structures. And if we now look on the left-hand side, on the very bottom left is the field for this day, or for this hour, for this time step, is the field, and we can see that the spatial structures are very comparable to the truth, or also to SAMOS in terms of what kind of spatial scales are resolved. If we look on the second column and compare the differences, we can also see that the differences are rather that we have some kind of worm bias in the GAN overall. If we compare SAMOS and GAN across the whole out of sample validation period, which was from 2019 to the middle of 2021, we can again see also in the error metrics in RMSE that we have those spatial structures. We have especially larger errors in mountainous regions. There are some small spots where the GAN, also in some of the southwestern parts, where the GAN has a lower RMSE in mountainous regions, but overall you can see that the error is of course a bit larger than what we have with SAMOS. And here we have again the similar plots for the mountainous region in the north of Spain, because the Europa, and we can see that the errors are from the GAN are a little bit more have a larger spread, and we also have a small bias, again the one bias that we just saw compared to SAMOS. And we can also see this on the right hand side with the box plots, that the spread in different time aggregation periods is a little bit smaller, and that we have the worm bias again. But what we can also see mainly in these figures, that we don't have a specific month or a specific season that causes problems, but it's rather a general source of the error. And with this, we're already on the last page. So probably many people here know the comic on the right hand side here. It's quite a common comic that you see in machine learning, where you make fun of this principle of just trying over and over again with more data to get the correct results. And this is in some sense also a part of the quintessential moral of the story that we had a little bit in this project, because we had some issues, some that we could tackle, some that we could tackle less so. So the main limitation, the main takeaway was that we had some time constraints and hardware issues. So to close the loop, what we initially wanted to do is to predict 3 hours, 3-hour time steps, the data, not hourly data, but 3-hourly data, and for 8 times, so 00 UTC, 03 UTC, etc. And due to the time limit, we only managed to complete the 00 UTC, and even this only with limited architectures. So again, some experiments with the units and the conditional GAN only with a smaller network size than what we initially wanted to do. So it's not as far as we wanted to do, but we still learned some lessons. So one point was that Samos already produces a very good baseline, which might sound intriguing because it's basically based on linear regression. But the reason why it already performs quite well is because we're using standardized anomalies. So we're taking away the fitted climatology and only predicting on the residuals. And this just works quite well as a baseline. And next, Irene mentioned already some issues with the topography or some interesting behavior. And the reason for this is also basically because of these standardized anomalies, because in the fitted climatologies, the topography is already indirectly included because we're using temperature, and temperature climatologies are dependent or are related to the topography, of course. So that's why in some sense in the units, it produced better results to not use the topography. Yeah, we still had some filtering artifacts in the units that we saw. And finally, for the conditional, again, the results were still like underperforming compared to Samos. And the output was sometimes a bit under dispersive. Of course, the solution, like also depicted in the comic, is to try a larger network, to try longer training, to use more training data. The training data was also a limiting factor because we split the training into these 3 hourly time steps, which meant that we overall, our order of magnitude for the samples was like 10 to the 3rd power, which is quite low because usually you have like 10 to the 5th or 10 to the 6th power of sample. So more training or more training samples would definitely help to couple these issues. Even though this might sound pessimistic, it was still good to just get a feeling of how these standardized anomalies perform, how well or how useful it is to use these fitted climatologies and predict only anomalies. And it was still, to some extent, successful in the sense that even though we used a quite small network, so for example, a couple of those that we tested here finished training in a couple of hours compared to the initially large network that we wanted to use, which would take a training time of 1 week for just one single model training step. And with this, I want to again thank you, ECMWF, for the opportunity to partake in this project. Thank especially the mentors that helped us along the way. And with this, we're open for questions. Thank you.
Yeah, thank you very much. I say Team Austria. So are there any questions in the room? Are there any questions on Slido?
No.
So I think we will have another presentation from the Spanish team, and then probably we can also take questions together for both teams, unless I see something wrong. Good, then thanks again. Over to the next project or the next presentation. Deep R. That's Antonio Perez Velasco and Mario Santa Cruz. And again, Mariana, you can introduce that team as well. Yeah, so me again. So basically this team was doing exactly the same thing as the previous team, but using slightly different methods. And so, yeah, as I said, it's really cool to be able to compare 2 different methods, and we've sort of got twice the work for just from one project. So that was really good. So with that, I hand over to you.
It's the one that is made permission.
Thank you, Marianne. So I first start with the team that has been working on this project. My name is Mario Santa Cruz. I study maths and did my master in statistics. I'm here with Antonio that studied physics and now is doing his PhD. We both work in Predixia. For those who don't know what Predixia is, it is a spin-off from the University of Cantabria, with more than 15 years of experience in climate services. We have a team that has a lot of experience in climate, remote sensing, high performance computing. And the other part of the team he cannot be here today, is Javier, because he is going to be that soon. So he's online, and he is PhD in engineering and works in the Institute of Physics in Cantabria. Now I move to the project descriptions. I will try to be brief, as it's the same project as before. We try to get ERA5 data to CIRA data. Why to use ERA5? Just because it's a product that is available real time with 5 days delay. Why to get CIRA as output? Because of its resolution. As you can see here, in the left it's ERA and in the right is CIRA. And this is then the border between Spain and France. The differences are clear with the resolution. This problem, we want to present an important keyword here, that is super resolution, that is transforming low resolution image to high resolution image. This is a keyword not used in meteorology, in climate, but as the models that we have explored during this challenge, we have to do a lot of research in literature, in computer vision, and this is the main keyword that we use, super resolution. But it's the same idea as downscaling. So now we move to the data. Just to be brief, here data is very important, and we have a lot of data, near 200 gigabytes. This data can be accessed publicly in the climate data store. And just a few steps need to be done to make ERA and CIRA uniform. As the main idea of this challenge are to learn things about the methods, how they work, and the dataset, we decide to decrease the problem domain from the whole Europe to just a small region, to can iterate faster in the design choices of our models. So we choose a region that has different ecosystems, as mountain regions, the Mediterranean Sea, rivers, or even islands. And now we move to the methodology, where I am explaining the methods implemented in our GitHub repository. We started implementing some basic interpolation methods that use only the surrounding pixels to produce the output. These are the nearest neighbor or bicubic interpolation. Then we also implemented in our GitHub repo typical convolutional neural networks. We have been widely used in meteorology and climate science. Another method that we don't implement in our repo, but is implemented in our partners repo, is generative adversarial networks that is also used for super resolutions. One of the main methods that we explore here during our challenge is the transformers, vision transformers. These methods have been very popular since its inception in natural language processing. They have been adapted to be used with images. And the last method is the diffusion models. As also the previous team, we have explored these models during the whole challenge and are implemented in our GitHub repo to be used for anyone. I will start explaining the noise models. As you get now an overview how they work, I will get into some details. These are the typical DALI, Midjourney, all that models. And I will illustrate the case of unconditional image generation, where we have zero images, and we start with this an statistical process. The idea is just we take the original zero image and we add noise for a finite number of steps. Normally it's around 1,000. In this process, we get to pure random noise. So the idea here is to reverse all this process. So we have a model that can produce from noise the zero-like fields, meteorological fields. And this reverse process, it's what is learned by neural networks. We train a neural network that learns to predict the noise added at each step. So we can use during inference the predictions of this neural network iteratively to take from input noise to the output grid. And the key factor here for super resolution is just conditioning every of these steps on the low resolution image. So the neural network will also take as input the low resolution image. And that's how we implemented the denoising diffusion probabilistic models. The other part that we explore is the vision transformers. And we implemented one of the state-of-the-art neural networks in computer vision, that is the swim transformer, with little variation to adapt it for our setting. Vision transformers are really powerful and are the ones that presented the best results in our challenge. One key factor here is that it uses a loss function that combines three loss terms, one in the prediction, one with the downsampled predictions on reference, and one with the blur predictions on reference. The idea of using the blur predictions on reference is to capture the high future details of each image and compare those high futures. And yes, here we use this type of network because it's more efficient than other vision transformer. Now a key topic here for this modeling techniques is the standardization, and this is probably the main difference between our case and the literature that we have read, because in classical computer vision problems, we are always working with RGB images. So the normalization is something very similar. And here we are working with different variables and we are working with different data. So here standardization plays a very important role. We along the project consider two types of standardization. The first one, in both we compute the mean and the standard deviation for each month in the training period. In one case, in the pixel wise, we compute those statistics for each pixel. And in the other, in the domain wise, we just compute one pixel for the whole domain. And now I present some of the details for the training, the number of parameters, around 700,000 trainable parameters, the learning rate, our sample, and the range of the data splits. Our models are available in Hugging Face, so you can see our Hugging Face, and you will see all models, both regular convolutional neural networks, transformers, diffusion process. There you can see training logs, where you can see how the models perform as they were training. And there are the technologies that we use. We use Python XArray for the data processing, and PyTorch for the modeling. Now I leave the floor to Antonio, who will explain the validation.
Here it's great. Good morning. I'm going to talk about the validation approach that we have followed. I have taken only images for the convolutional swing transformer, which was the model that obtained better results. For the validation approach, we make the inference over the testing period from January 1st, 2019 to December 31st of 2020. We have two main approaches. The first one, in which we consider the entire geographical area for making spatial maps, and the other one in which we take specific locations of interest that are all over the area. These are Madrid City, Barcelona City, and some specific mountainous regions that be for interest for the validation, like Mulhacén or Anet in the Pyrenees. As a baseline, we have used the bicubic interpolation because it is smoother than the bilinear or the nearest neighbor. The results for convolution for our convolutional swing transformer are remarkable. We are able to reduce 35% the mean absolute error of the bicubic interpolation, and nearly 30% the error, the root mean square error. On the top side, you can see the difference of the metric as an absolute value, and on the downside, you can see the difference of the metric as a relative value. So we mainly perform better than the bicubic interpolation all over the region of interest. These are some samples that have been taken randomly from our testing set. We can check that the bicubic interpolation has not present the small artifacts that Sarah or our model predictions present, and which are of interest in this super resolution task. We also want to assess the versatility of our models by taking diverse regions such as the Mulhacén. Here we are presenting just two of the specific regions that we validated, but there are a lot of figures, and we have them available if you want to check them out. For instance, for the regions, mountainous region of Mulhacén, we can see that the error distribution is almost around 0. And for the Ibiza island, we also are closer to 0 than the bicubic interpolation. This is also shown in the time series as well as in the box plots. One of the key factors of this model is its sufficient inference speed. We have added a video in which you're not going to be able to see it, but it is a video in which we took a month of 3-hourly steps, like 248 samples, and the inference procedure was completed in about 21 seconds in my local environment, just a normal PC. Also, an important factor here is that with this method, we are unlocking Sarah-like data access. What I mean with this is that Serra is an static dataset. There is only data from, I think, 1985 to 2021, to June 2021. So it is not updated frequently as ERA 5. What we have done to show this important factor is we have downloaded the ERA 5 August month of 2023, and we have downscaled with our convolutional swing transformer the data to the Serra resolution. For being more specific, we are gonna take a look at one of the heat waves that were in our location, Santander, which reached its highest temperature of 41 degrees on 23rd August. This is the Serra estimates that we obtained with our model, and this is the ERA 5 data. It looks good. The infrastructure used has been a virtual machine from the European Weather Cloud, and also a virtual machine from the Artificial Intelligence for the European Open Science Cloud, which is a project in which we are participating. In both of them, we have access to a GPU, and it makes much easier to train the models. The implementation has been open source. All the code is available through our GitHub, and we are more than open to collaborate with anyone that wants to keep working on that or whatever. The project conclusions, we have made a super resolution success. We have trained a convolutional neural network, a diffusion process, and also a vision transformer to try to downscale ERA 5 data to the Serra resolution. There are general metric improvements, as I mentioned before, with a 35% improvement in the mean absolute error, and also nearly 30% in the root mean square error. And also our model excels in diverse regions, from mountains to islands to coastal areas and so on. The next steps in Predictia, we have research projects in which these methods can be implemented and can be useful. So we want to keep working on this. We could try to improve the performance using different normalization schemes, which we really think that are crucial in this type of modeling, and also explore opportunities to make the model bigger, as we only used like 700,000 parameters, and there are models out there using millions. Also expand the modeling coverage. With this, we have two things in mind. Incorporate variational encoders to reduce the data dimensionality and fit the model with that output of the variational encoder, and also use patches instead of the entire domain. We could try to predict different variables such as precipitation or wind. We have only tried with the temperature for now, and it would be good to have this in a production environment where you download the ERA 5 data in real time and you make the Serra estimates in real time as well. This is a thank you slide to Marianne and all the mentors, Matthew, Andras, and Cornell. Also to the ACMWF and the code for our team, like Esperanza and Athena, and also for our source providers. And that's it.
Thanks so much. The team Spain. My question again, as after every presentation, are there any questions?
So you did try the diffusion model as well as transformers. So I had two questions for this. One is how much of a difference in the performance of these two models, and how much of a difference was in the training time for these models? Yeah.
Big difference. Yes, we spent like 80% of the time of the challenge with diffusion processes. But yes, probably people that have not worked with them don't know about how hard it is, because even when you are training a diffusion model, you are training at the noise network. So until you don't go to inference and use that in a testing environment, you don't know how it is performing. So the iterative process in the diffusion models is so slow, just not the modeling. The modeling was also slow, but probably like 4 times more than the convolutional transform. Also the inference. And the inference is also, yeah, the inference there is a lot of things to do to improve the computational cost during inference, but as we didn't get to the best result, we didn't spend time in optimizing that inference of the diffusion models.
Thank you. That's also maybe a question to both teams. This is the last one. Did you use, maybe I missed it, but did you use any other higher resolution data sets input into the training, like topography or land cover, for example?
We tried, we explored the difference, but the key thing in our problem is that we are working in a fixed domain. So the orography is something static over all samples. So if you are using a good model that has a lot of computational modeling capacity, that should be learned. And we check that because we compare our model without using orography and using orography and using landmass use. And the results were similar in terms of error, were really similar, and there were an increase in computational cost as you have to train samples with a larger size.
Thank you.
The Austrian team, do you want to answer, Sven?
Yeah, so we tried using it and not using it in all of the different models. So just to reiterate, for Samos, we didn't test it yet, so we don't know how much it would have improved the baseline to include the high resolution topography. For the UNet, it didn't help the results, so it worsened the results, which again is mainly due to us using the standardized anomalies and the topography being included indirectly in these climatologies of temperature. So it's basically the issue is because or it relates to the use of temperature in this problem. But for the GAN, the results, we didn't test both versions, but we used the high resolution topography and the land CMASC for the GAN, and the results were already quite promising. So I don't know if it would have been even better without it, but since the results didn't have any strange artifacts or something else, I would assume it was helping the GAN to use this high resolution information. So yeah.
Can I add one thing to the question? For example, for one of the next steps, we are thinking about a patch-based strategy where we are working on different domains, and in that case, it's crucial to add the orography. But instead of orography, we add another variable that has more signal. That is the difference between the high resolution orography and the interpolated orography of IRAPAD.
Yeah, hi, thanks, really cool stuff. Niklas from Sketchbook Earth. One question, you mentioned you would like to extend that to other variables, like for example, precipitation, and temperature tends to be more homogeneous, no, like spatially. So would you expect similar good results for precipitation? And if not, what would you think of trying to overcome this?
Yeah, precipitation is quite different from temperature. You have to take into consideration physical constraints. Normalization is going to be different. But for example, we expect that baseline methods like interpolation, by cubic interpolation, do not work as well for precipitation. So maybe the models perform worse, but also the baseline methods and the results are more comparable in that case.
Yeah, I give the question of the Austrian team. You need the question again?
Yeah, sorry, please repeat. Precipitation, yeah. Now yeah, I guess it depends very much on the model architecture as well. So like if you compare UNet to the GAN, for example, UNets are generally prone to produce a more smoothened output or prediction. So it would probably have a little bit more issues with non-homogeneous quantities like precipitation. But on the other hand, the GAN, for example, produces something out of noise, basically. So it's in some sense comparable to diffusion models. And it has inherently not that much of a problem with like smaller scales structures. So if the prediction in terms of absolute values is good or not, it's surely worse than temperature would be my guess. But at least in terms of like metrics, like the power spectrum, the spatial structures, those would be easier to capture with a GAN. So it very much depends on the architectures that you want to use for specific quantities, I think.
And for the SAMOS approach, so the colleague who started with SAMOS is doing something similar for precipitation for various time ranges, but he's not using SAMOS per se, but more like the GMOS, the global MOS approach in that case. So there are differences, like he said before already, with the normalization, with treating of the data. And so you couldn't just use it and play around.
Thank you. Any other questions? Okay. Yeah, then I ask you to please stay here for just a second. Would like to know this to the audience that is listening online. Thank you. Another round of applause. So we had a very exciting morning session, I think. We started off with fire forecasting, then was benchmarking surface heat fluxes. We heard about diffusion models on WeatherBench, and now the last reanalysis project has arrived in DeepR. We are going now in the lunch break, and we resume at 1400 CET. So I hope you will join us online later. And we take a group picture, therefore you have to stay here. So Ruben, we can go offline. No? Yes. So do we have anyone on Zoom? So if we manage to have some colleagues. Yeah, so we take a group picture here with people on Zoom, and then we take one downstairs. So everyone here?
Yes. Please, everybody come down. We'll like make like here some people.
So the people who are online, if they can. Yes, if people online can turn on the camera, so they will be in the picture.
Everybody move back.
Yeah, just a second.
No. So, what do we get at now?
Sorry.
Can we get the camera on our team now? So she's on the screen. She's taking some photos.
Yeah, do that. That's perfect. Yeah.
And we will take another group picture downstairs in the yard with. That's my. But then you see us on the back side. The net. Yeah, make that.
So I need a bit, like, why don't you rise over there?
For 5 minutes.
3, 2, 1.
1, 2, 3.
Now give me like a.
It was my candiest. So small. That's just waiting to risk.
1, 2, 3.
And in the summer stage, you're only love and more. You are.
Let me just put the music and the
I really like. I like, you know, generally the colors and everything, it's.
children, would you listen to me? I'm a friend, ain't trying to run your life, believe me. Just don't mean nobody no good, believe me. Should have been called devil's dust instead of, believe me, children. And that was when he could have sworn the room was moving. But that was only in his mind. He was sailing. He never really seemed to notice part of the high, the sweat was pouring. He couldn't take it. The room was exploding. He might not make it. Please, children, would you listen? Just ain't where it's at. You won't remember what you're missing, but down some dead end streets there ain't no turning back. They were standing, everybody in a circle, the whole family, listening to the preacher's words. Sis was crying. She alone held the secrets about his dying. Tears falling to earth, and maybe her fault. He was so trusting, God only knew why. They were dusting. Just ain't where it's at. You won't remember what you're missing, but down some dead end streets there ain't no turning back to back to back to back from. Take it. The room was exploding. You might not make it. Please. Children, it's hard to listen, but I ain't trying to run your life. Might just seem like one more good time, but down some dead end streets there ain't no turning back.
Maltratei, sim, maltratei. maltratei demais. Me machuquei, meu coração que bate calado, 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 que bate, bate. Oi, 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 oi. Maltratei, sim, maltratei demais. Me machuquei, meu coração que bate calado, 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 que bate, bate. Oi, 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 oi. Que bate calado, 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 que bate calado.
You sang the marquee here. From very end, you knew the cost. It was a temporary fix.
desire, spirit desire.
All you've got is this moment. 21st century's yesterday. You can care all you want. Everybody does, yeah, that's okay. I need you tonight, 'cause I'm not sleeping. There's something about you, girl, that makes me sweat. So slide away and give me a moment. The moon's not so raw. I've got to let you know. I've got to let you know. You're one of my kind. So slide away and give me a moment. The moon's not so shine like eyes. Look like night sky. The moon in silver dreams. Always down in peace. Lighting up our night.
watie tutyoborwa watie tulengezwa.
Ça va boucher ce soir. Toute la soirée, on va danser, on va goûter de bonnes choses dans la vie. On va boire trop. On fait la fête de semaine. On va faire la fête de l'année. On va faire la fête de l'union. Tout le monde vient ici. Viens. Mon ami, il faut que tu fasses doucement, tranquille, faire doucement. Amis, ça marche, ça bouge. On a dansé. On a bu. Et ça va. Il y a déjà beaucoup soirée. On va faire la fête. On va faire la fête de l'année. On va faire la fête. Tout le monde vient ici. Viens.
Across the ocean, leaving just a memory. Snapshot in the family album. Daddy, what else did you leave for me?
was feeling kind of lonely. Then summer came my way. I was feeling kind of lonely. Then summer came my way. My way, my way, my way. Summer came my way. My way, my way, my way. Summer came my way. I was feeling kind of broken. Then someone came my way. I was feeling kind of lonesome. Then someone came my way. My way, my way, my way. Summer came my way. My way, my way, my way, my way. Summer came my way. I was feeling kind of lonesome. Nothing left to say. A beat without a drum. Then someone came my way. My way, my way, my way. Summer came my way. My way, my way, my way. Summer came my way. My way, my way, my way. Summer came my way. My way, my way, my way.
the need to cry out loud. I'm lost in the crowd. I don't know where to go. I don't see no one I know. At the party we had a good time. Lots of people were there, they were friends of mine. And they told me to play for my best friend. Yes, she did. Oh, yes, she did. Yes, she did. Oh, yes, she did. Yes, she did. Oh, yes, she did. Yes, she did. Oh,
red light on the machine, so I know it's rolling. I can see the red light on the machine, so I know it's rolling. I can see the red light on the machine, so I know it's rolling. I can see the red light on the machine, so I know it's rolling. I can see the red light on the machine, so I know it's rolling. I can see the red light on the machine, so I know it's rolling.
Wasn't so long ago, I had given up all my hope, convinced that love was a game for fools. People just changing up all the rules. To me on the fly, I saw the future in your eyes. Must have sensed my pain or heard my plea, like an angel sent straight here to me. And I hope and pray every day I will always feel this way. Now my karma must have been in check. You're much, much more than I'd expect from a world I thought was full of deceit. You turned it all around for me. Never give up on love again. Sometimes it's there in front of you, but all you see is a small real room. So take a chance and step on in. You won't know till you begin to put your faith on higher ground, where love is lost, it can be found.
I can see the red light on the machine, so I know it's rolling. I can see the red light on the machine, so I know it's rolling.
Makes me wanna clap my hands.
Come on.
They met one day in a summer storm. Her senses told her that it was wrong. She was a young lady of 23. He was a child of technology. The scientists hadn't planned it this way. They just wanted to break out for a day. But their mistake was just too plain. She refused to listen as he explained. I'm a little man. I made the wires. I'm an old man. I'm an old man. There ain't no way that I could ever love you.
You maybe yes. So,
I can't think myself. Yeah, you tell me. Okay. Hi, everybody. Welcome to the second part of our event, Final Call for It 2023. I would like to welcome especially for those who are attending remotely online. And after every team presentation, there will be a turn of questions. So those who can add something to the team, please connect to Slido and ask your question, and they will be please willing to ask. There will be 5 more presentations after this break, and the first one is the project's Atmospheric Composition Data Explorer. One of the mentors, Micha Ratzinger, will introduce the team and the idea behind the trend. Micha, it's yours.
Yeah, if you have an idea, but otherwise, I should try to share it.
Oh, you want to share on yours?
No, I don't think. Yeah, so thanks very much, Esther, and welcome to the afternoon session. So just a brief explanation what's behind this challenge. So we publish, I'm working for CAMS, Copernicus Atmosphere Monitoring Service at ECMWF, and we publish around 3 petabytes of data to the Atmosphere Data Store, and some of the data that we serve is not that nice, not easy to work with. So like all good ideas, this one was born out of the laziness. So we want to simplify the kind of workflows that we use, me and my colleagues, to generate some of a bit more complicated product that we produce on regular basis. So we wanted to start with very simple kind of workflows that we can replicate some of the typical products, but then hopefully we build these kind of components on the way that can then be generalized and reused. So it was really nice experience working with with the team here, and I'm looking forward to your presentation. Thank you.
Now we go to share. But do I
present a slideshow. Hi, everybody. We are looking for challenge 11. And well, as was already mentioned, our project is called Atmospheric Explorer. And first, of course, we'd like to thank all our mentors. You can see we've had many mentors, and especially we have coordinated this very big team. And of course, Esperanza and Latina and everyone who was involved in organizing for us. So first, we'll quickly introduce ourselves. I'm Elisa. I currently work as data engineer, and I also worked as mobile app developer before, and I studied physics. Luigi studied physics as well, and we were colleagues a few months ago, and he also is a data engineer and data science scientist. And then Julia is recently started her PhD in environmental engineering and also studied ecology and natural science. So a lot of different backgrounds. And first, I present a brief table of contents of what we'll go through today. The background of this project, which was already a bit, well, the goal was already introduced by Micha. The challenges we faced and the stack with which we tackled them. And then the most important part is a live demo of the app, and of course, time for questions and answers. So yeah, the goal was to develop an interactive application to create these atmospheric composition diagnostic plots on demand. Because as Miha mentioned, there are these very big data sets, and we might want to explore the data sets, understand better how they are made, and the data quality, for example. This project was inspired and followed in some way another project from last year's Code for Earth, which was called Atmospheric Emission Explorer, which was also an interactive application to create plots, but from different data sets. And the idea behind this challenge was also to create a generic framework for different data sets. So currently we use 2 data sets, but the idea is that these APIs can also be reused in the future for different data sets, possibly to also create other plots. And another key feature of this project is that this tool could be used by many different users. So for example, researchers at ACMWF that might want to explore these big data sets, but also outreach users that want to create plots for their papers, for example. So this tool must also be flexible enough for all these different users. And now with this switch,
Thank you, Elisa. So to reach, to reach the final outcome, we have to reach 3 different products that are the modular pattern APIs, which allows to download, interact, and produce plots with some functionality. And also we made a UI, so user interface, that is an interactive interface for users to interactively select on the map an area or a countries or a continent on which they want to deep and investigate for some atmospheric variables, and as well a command line tool, so it's live. These 3 products will be better described later with Elisa. And here I'm showing the 2 main kinds of plots that can be produced with this app. We have on the right, like the time series plot. So we have, you can choose different kind of variables depending on the different data set. We have a lot of variables that are possible to plot as time series. And here reported for the time series selected, the average value for the area selected on the user interface, and also the confidence interval, which tend to keep in account the spatial variability within the area. In the left, we have like kind of Moller plot, which is a specific plot. Here is proposed the total column ozone. So we have on a time series selected for the variation of ozone. On the y-axis, we have, for example, latitude. So for each latitude, we can see on average how it varies during time. But of course, this kind of plot can be used also, for example, considering not only latitude, but the stratification of atmosphere from the bottom to the top, considering so different pressure levels or modern levels, and see how, given, for example, concentration of gas vary during time for each pressure levels or model levels. So the technical challenges are mainly 2. The first one is the kind of data sets that we consider. They are the CAMS global analysis and the CAMS greenhouse gas fluxes. These 2 data sets are different for different reasoning. We have different time availability, different spatial definition, and as well inside CAMS greenhouse gas fluxes, we have different spatial definitions. And also the variables considered, so atmospheric variables are different. That are many, so much more in the CAMS global analysis, and less and mainly focused on fluxes for the CAMS greenhouse gas fluxes. Anyway, the most important difference is that the 2 data sets have different file format. Both have an HDF file for the data, but they are structured different. So it was a big challenge to have a more generalized
function and also for the user to have just one generalized user API. So the users don't have to think on which data set they are using. And so starting from this point, there will be future applications for a more generalized use for different kind of data sets. Another technical challenge is the fact that we faced with the geospatial data. So not ordinary data sets, but also with geospatial components, both for the APIs, so the functionality for considering the average value and confidence interval and producing plots, but as well for the user interfaces, so the possibility for users to actively and interactively select on the map the countries, the continent, or a specific area. So now we move to the technical stack with Elisa.
Yes, so these are the tools with which we face, well, we solve these challenges in a way. And of course, they are the main Python libraries we use in our project. For the API side, we use Xarray, which is the most popular library to read and sample CDF files. Then GeoPandas to manipulate the geospatial data and especially the shapefiles on which users want to plot the data. And then for the plotting APIs, we use Plotly that allows user to create interactive plots. So this makes the user interface for the interactive application even more interactive, because after creating a plot, you can even zoom it and change it in some way, customize it, and then saving it as you want. And for the user interfaces, we use the Streamlit for the main application, so for the UI, which is a front-end Python framework to create easily into like applications that can easily be interacted with. And then click to generate the command line interface, which is the interface you can access from the terminal. And click create this tool directly from the API functions, also with all help strings for understanding on the terminal what you need to do with this tool. But now I guess you will understand these applications better with the live demo, which, as it's a live demo,
Thank you. Usually, yeah, live demo is a terrible idea. So we'll try our luck here. So hopefully you can see my terminal. So as mentioned by Elisa and Julia, the application is provided as a Python package, so you can easily install it on any virtual environment. We also provide a Conda environment for installing it easily using Conda in case you use Conda, but you can use any kind of environment manager. The idea here was to very briefly show how a user would use the UI, the CLI, and then talk a bit about the APIs. So once you install already installed the Erdor, so I already created the virtual environment. As you can see, I already installed the package, so I spared you the boring part. How would you use the package once you have it installed? So we have the main CLI entry point, which is Atmospheric Explorer. As you can see, once you run this command, you can see the help, which show you what you can do. So let's try the run command, which runs the Streamlit front end. So as you can see, the front end has started. So the front end starts on the home page, which allows you to do the main geographical selection. So you will be able on this front front page to select ones. I'm very slow, sorry, my PC is in power setting mode. So you can select any kind of geographical entity from the continents level to, sorry, that's why live demos are not a good idea. Continents, organization, countries, and subnational divisions. So here you have both a way of selecting them through this, this selector, or you can also, so one would, for example, select Africa and run the update selection. And here you can see, just give it a moment, you can see the map is updated with the selection, or you can also select directly on the map, for example, North America, and the selection is also updated on the sidebar on the left. So once you have done your selection, you can also, oh, I should mention, you can also select free shapes. So if you switch this checkbox, you can also select free shapes on the map. But let's try selecting, for example, a continent, which is a bit more interesting. Of course, there is some kind of conversion. As you can see, I switched from the free shape to the continents, and basically what the UI did was an intersection between the continent polygon and the free shape. So I have Asia and Europe selected, which correspond to the previous shape. So now let's try to generate a plot on the fly. So here is the yearly surface plot, which plots the yearly surface fluxes for example, carbon dioxide. So let's select just a few years, not too many, because we don't have that much mobile data. So once on each page, you have, as you can see, a selection box where you can select different kind of variables for each kind of plot and for each kind of data set. Here you can select, for example, the year, the years, the data variables, and the kind of variable you want to generate. Along with you can specify the title. For example, here you can see the fossil emission for carbon fossil fuel, for carbon from fossil fuels sources. So here the plots, as mentioned by Elisa, are fully interactable. You can select them and zoom on the plots, and you can also, of course, save them as a static image to be used on any report or PDF files, for example. You have here the other pages for the other kind of plots. And of course, you can do all of this also on the CLI. So let's switch to the CLI. So the UI is mainly used for prototyping and exploring the dataset and generating different kind of plots on the spot. For programmatically generating plots, the next step would be the CLI. So as mentioned, as you've seen before, you can run the main entry point command, and it will show you the two main commands, which are the run to run the Streamlit app and the plots API to generate a plot. Here I have already a plot command ready. So as you can see, you have to call the plot command and the anomalies subcommand, and you have to pass a bunch of options to the command. So how do you know about these options? How would you guess which options you have to pass? Of course, each CLI command is provided with a comprehensive help, which tells you all about the commands you have to pass, the options, and in some cases you are also provided with all the possible values for these options. Here I already showed you this command. I already generated the plot beforehand because I didn't want to try my luck twice. So here you can see, sorry, wrong place. It should be this one. No, this one is the one I saved before. It should be this one, sorry. So here you are. This is another kind of plot. Of course, the plot is very, very uninteresting because I downloaded a very small amount of data. And as you can see, this is the total chromosome by year, pretty much, for different times. So next, with the CLI, you also have some utilities. As you can see, you also can explore. You also have the data and logs commands. So these are utilities which are provided to keep track of all the data you have downloaded, and to, in case you need it, to clear them, to keep the amount of data low, and same thing for the logs. You have the clear and list. So the next level, let's say, is the APIs, of course. here I won't show you how to use the APIs, but what we focused as Elisa and Julia mentioned was to make the API modular enough to be reused. So the most important thing was to document them well enough so that anyone could you know, hands-on start developing on them. So we provided a full you know, README with a quick start on the APIs, where we show how to generate plots on the fly using the data interfaces for the different kind of plots, and using the plotting APIs with the full description. And also we provide a comprehensive documentation of every single class, every single function defined in the APIs with the docstring and descriptions. And yeah, I think this is it. About the next steps, maybe a few words. So the application as is can be already used. So we had like some nice to have that we weren't able to provide in time by the time like the 31st of August. So we had some nice web like the caching for files, like the ability to for the application to cache files and keep track of which files, which data has been downloaded. We already have, like we will keep working on this, and we already have an in-memory caching working for the application, just we couldn't provide it in time. And there is also another ongoing approach for on-disk persistent caching. And so if anyone wants to help with it, it's everything is on GitHub, of course. Any contribution is welcome. So thank you very much.
Thank you very much. Thank you very much. Very good. Thank you. I don't know if there's any questions.
Yes, and thank you. It was a very nice presentation. I have a question. You use Streamlit for the user interface. What is your, I don't know, what is your experience with Streamlit? Was it easy to use? Did you take the decision to use it, and how you compare with other tool, if you had to?
Yeah, I mean, about Streamlit, we have mixed feelings. The Welfare Explorer used the Voila for the UI, and I think in some like respects it's way easier to work with, because it just, you know, it's a notebook which is basically transformed into a web UI, into a web app. So in some respects it's easier because each block of code can be run by itself. We decided to use Streamlit because we were a bit more comfortable using Streamlit, and also we think it's a better looking interface. But we had a lot of challenges with the map, because basically Streamlit tends to update in an eager approach. So every time you change something, Streamlit just updates. So with map, it was pretty much impossible to work with. So we had to control how the map was updated using some other extensions in order to make it usable pretty much. And yeah, so it's a bit, I think Streamlit still has its drawbacks. For example, you don't have many tools to control the flow, the update flow. But on other respect, it was better because it has native widgets and all the components you need to build a web app pretty much. So mixed feelings. Thank you for your question.
Yeah, thank you. One brief question: does Streamlit also allow the user to download the data that is shown, that is plotted, like a bit like in our World in Data, where you also have this option to, you see the plot and then you can download the data which is plotted?
No, that's wrong.
Okay, that is in Plotly. Okay.
The thing about Streamlit is that it's integrated, it's well integrated with the main plotting libraries like Plotly. Also, there is PyLab, which is a very good library for plotting the geospatial data on a map, pretty much. And it has an analytic integration with that, with them. So what we did was leverage this integration to generate like native Plotly plots, which are embedded into Streamlit. So that's native Plotly pretty much. And the API basically work with Plotly videos. Or maybe I didn't understand.
I think when you put download the data that you do.
Yeah.
I think it's just something we can implement, but possibly it's too long.
Yeah, I mean, you could actually not on the UI, but I mean, we didn't implement the possibility on the UI. Of course, you can on the APIs, of course, yes.
Yeah.
Yeah, that's a good idea. Actually, we had another feedback about finding also the Averta team code to maybe on the UI you want to explore the plots and you then want to produce hundreds of these plots. We had a feedback about providing the Averta code to generate these same plots using the APIs.
Yeah.
So there wasn't enough time to do that, but we plan to keep working on it. All of these, like improvements.
Yeah.
To make it much better to work with.
Cool. Okay, thank you.
Thank you very much. Thank you. And now I would like to introduce another project. 2023 is the sketchbook illustrated climate chronicles. One of the mentors is here with us to introduce the team and the idea of the project behind the challenge. Rina Rossen is with us. Good afternoon. Okay. So climate change is currently the largest problem humanity is facing. And this became even more relevant in recent years with the increase in extreme climatic events, not somewhere in the remote part of the globe, but also here in Europe. As part of climate change service, at ECMWF, we produce climate bulletins on a monthly basis, describing the state of the climate and highlighting and explaining extreme events, not just in Europe, but globally. Also, together with our partners from European Met Offices, we produce executive summary of yearly state of European climate. The software and the data processing techniques we use are our internal ECMWF, and this makes it difficult for other users to reproduce our data and visualization. So the main purpose of Sketchbook Earth Challenge is to produce Jupyter notebooks with training material, explaining how to process data, how to calculate various quantities, and how to visualize using open source Python packages. So I'd like you to welcome Nikos and Niklas, who will explain Sketchbook Earth.
Yeah, thank you. Thank you, Irina, for introducing. And my name is Niklas. This is Nikos. Eddie, our other mentor, cannot be here today, but also thank you to him for support through our journey. I think, yeah, when we're right now trying to get up the. Yeah, we also. Yeah. So I hope you did not use all the luck for showing live demos, because we also needed. Yeah, great, cool. So, and actually now I already need your support to switch the screens, because now, before we head into this presentation, I would like to get a little bit interactive with you. So please get out your mobile phones or computer, head over to Menti. And when we go now to the next slide, you still will see the code, hopefully, on the screen. And then try. Oh, I already see people voting. So you probably already see the question, which is really great. We don't see it here yet, but you apparently see it online or when you hit the Menti. So the question is, will you find more sea ice in terms of the rear? A, in the Arctic, B, in the Antarctic, or it depends on the season. So we see now the results. Cool. So it's quite mixed. Yeah, we'll wait a bit more, but maybe somebody who's for Arctic, maybe can you raise your hands? Arctic, anyone here Arctic? Okay, some very shy hands there. Antarctic, are you more brave? Yeah, a bit more brave. Why? Anyone wants to tell me why Antarctic? Just a feeling, gut feeling? Yeah. Yes, great. Actually, I also thought in the beginning it would be more Arctic, but now when we see the results, maybe you can show the final answer. You see it. So the final answer is it depends on the season, which you will also see in a bit. And to be clear, I mean, we're talking about a fair comparison. No? We're comparing like Arctic winter to Antarctic winter, so not like January to January. Okay, so let's go to the next question. Last one, yeah, and then I get started. Do you know what is the current sea ice extent anomalies in the Arctic and Arctic in terms of standard deviation? So if you have like 0, it basically means, okay, that's what we would expect right now. And I think you have a range from -5 to 5. You think about your Gaussian distribution, like ±2 is already you're at the outer edges of your distribution. Everything beyond is really extreme. The reference time frame is going, good question. It's from 1980 to today. No, it's a reference period. Oh, sorry, 81 to. Is it? It's the current it's a current reference period, 91 to 2020. Climatology, yes. Okay, I see the answers are trickling in. Interesting. Okay. Okay, I see, but already from the results, I can see you follow the news. That's cool. So we have like a couple of more seconds to go. And when we hit now the final answer, so yeah, we are. So, okay. So we try to remember the names, the numbers, but we'll get back to it at the end of our presentation, and we'll actually derive the answer hopefully live. So let's see if it works or not. And now we go back to. Okay, cool. So here you have the answer for the first question. You see this animation showing the sea ice extent in the Arctic and the Antarctic from 1990 to 2020. And you can see, just note briefly that the y-axis has a slightly different scale. So for the Arctic, it goes up to 20 million square kilometers, while for the Antarctic, it goes to 25 million square kilometers. But you can see that in September, so the Antarctic winter, we have more sea ice compared than in the Arctic winter. And in the Antarctic summer, we actually have less sea ice than in the Arctic summer. And I already figured from the responses that you gave that you have also like followed the media. So you have probably seen that this year was very terrible for sea ice extent in Antarctic. For the first time ever, we actually have really extremely low values, and it was reported by The Economist, BBC, The Guardian. And you can see from the figures, well, they are basically showing the same, more or less, data, but in a different way. So the question is a bit, if we want to report on these climate extremes and these events, where do we get the data from? And Irina already introduced it a bit. One of the prime examples, in particular for Europe, but also globally, is the Copernicus Climate Change Services. And they provide, basically, they provide intelligence reports about climate events. And in particular, they have 4 categories or 4 columns. The first are the monthly climate bulletins, which shows monthly updates of global, but also European, Arctic, and Arctic climate situation. Then we have an annual report about the European state of the climate, and also on an annual basis, the climate indicators, which are more like broad-term indices describing the overall climate on our Earth. And finally, a report also annually published that focuses on specific events like heat waves in Canada or wildfires. And just to give you a brief idea of how it looks like. So if you would go right now to the climate intelligence section of Copernicus, and then open the climate bulletins and go to sea ice, then you will find this figure. I just converted the colors, but it's really just like copied this figure, basically. And you can see that Antarctic sea ice extent was dramatically low this summer. So at that step, I'd like to take a brief step back and think about who is possibly interested in this information in our society. And you can think about 6 categories. So we have scientists, we have educators, teachers, professors. Then we have environmental consultants. We have journalists or media outlets, policymakers, and obviously also general public. And I'd like to think about the target audience sometimes also in a different way. It's actually, it's not too complicated. You can think about it in the one dimension is policy influence, like what is the potential of the target group to influence our policies, and the other is science literacy. So how used is the target audience working with scientific data, with programming and so on. And the general public, well, you can argue about policy influence perhaps, but I would say it's rather low on both scales. But then the other categories, you can more or less like plot them on a line. And well, don't pin me down on this figure because it's really qualitative, you know, it's like, it's not very scientific. But in general, you see that scientists clearly have like a high degree of science literacy, but then you go down the chain to educators, environmental consultants, journalists, finding policymakers. And our project basically tries to improve this information transmission from going from the one dimension to the other dimension, so increasing basically how to transmit the information from scientists to the policymakers. And to make this clear in one example, so let's take one particular example here. Consider you're a journalist and you want to report on this year sea ice reduction in Antarctica. And so you go to the climate bulletins, you see this figure that we already seen earlier. You think, okay, wow, very extreme. I need to bring this out to society and I need to tell the story. But well, first is I see the data only goes until the end of August. Now we're almost at the end of September. So I need the most recent data perhaps to see if it also continues the trend. And how can I reproduce the figure? Because Guardian, BBC, they all have like different corporate designs that they have to fulfill. And this is what we then created in our challenge. So a solution that allows users to reproduce different figures. And there are 2 main characteristics. So first, it must be fully reproducible. So we only use open data from the Climate Data Store, Atmosphere Data Store, Marine Data Store, open infrastructure. So Jupyter Notebooks, Binder, Google Colab, Wikio, and open software. So the entire Python environment
which, yeah, with the common packages from Xarray to CartoPy and Matplotlib and Seaborn. And the second characteristic is it must be transparent. So we not only want to deliver recipes, but also make clear and explain exactly step by step how to download the data, how to access the data, what are the necessary steps to pre-process the data, and finally to visualize the data in the way that it is shown also in the climate intelligence reports. And in all this, we tried to follow with this approach of having like simple instructions, but yet flexible enough so that the user can really use it, and it really adds value to users. So here you can see the final results. You can find the book published at ECMWF codeforEarth.github.io/@earth. And just to give you a brief example, like when you will go through this book, you will find what I mean with flexible, specific code cells that allow you to define your region of interest or to adapt the climatology reference period to your needs. So then more bit in concretely, what can you find in that sketchbook? Now you can find how to reproduce selected figures from monthly climate bulletins, climate indicators, and the ESOTOP report. We show in these tutorials how to pre-process different climate variables, so ranging from greenhouse gases, CO2, methane, temperature variables like sea surface temperature, but also surface temperature, sea ice, sea level, and how to derive indices of large-scale patterns, in particular here ENSO and the North Atlantic Oscillation. And finally, also a dedicated notebook to how to create interactive plots and animations, something that goes also in line with what we've seen from the group before. So you can see check out the video here, but I think more interesting, okay, that will come afterwards. Just one more example, which also showed like during last presentation. So if you would go right now to the climate intelligence reports of the Copernicus and click on climate indicators and then go to the greenhouse gas section, you will find this figure here, which shows the global concentration of atmospheric methane together with the annual growth rates. And you can see here on the right-hand side our reproduction that has like the entire associated notebook at that link here below the figure. So, and now we will go to a live demo, showing you how, like giving you one example. I cross my fingers that it works. You can also, if you like, if you have your computer online or maybe even with your mobile data, follow the instructions. It's the example that we plan to do just will take a couple of megabytes. So that should work. And I would hand over at this point to Nikos.
Hi again. From my side as well. So let's try to see that we are also liking like the previous thing. Let's go to the link. So this is how the notebooks look like. This sketchbook we have created. We have a background on the objectives. Normally, for every book, you can see links to the relevant reports or the bulletins where the plots are made from related to these particular reports. We refer about which variables we're going to use. Yeah. I have some nice overview data sets where you can find the data. They are available also in the CDS and Climate Data Store. And here also we have some links that you can run for this book also in the cloud, not only locally. And let's use Google Colab in our case just because it's a bit faster. Here you see also we have some information about how to run code. So it's the same book as before. Now it's just that we will start running it here live. And just because we are in the Google Colab, we need to add some libraries. So bear with me for that. So that's the only drawback if we collab. That's suppose this. I didn't prepare Italian course. I'm sorry. Anyway, till it makes the installation, hopefully, we can maybe have a look a bit at how the more, let's say, user-friendly version looks like. And the thing you can start with maybe, of course, is how to execute all these books, either again in the cloud, with Binder Google Cloud, which again here we need to install some libraries which are not installed in the environment, or also in the local machine. You can clone the repository that is on GitHub. We have also the environment with all the libraries needed. Takes a bit of time. So what Nicholas mentioned, we have these different sections, the greenhouse gases. And these are two, let's say, chapters that give some information about, show us how to download data, for instance, from the Planet Data Store, how to process, and at the end, we have, for instance, some of the figures, like what exactly we showed before. So you follow such a tutorial, you can have this particular plot. Maybe this is still taking some time, but I think we will make it.
Where this is going to be installed,
to the actual one, right? Okay, yeah, let's maybe have it here. So what we plan to do now, which we will do, is okay to install the packages. So the first section, the important packages, make some configuration for the DAS, which is not needed actually for our particular case, but for the rest parts of this notebook is important because there's a lot of data. So we need to chunk it and use DAS for memory efficiency. Here, it's again what Nicholas showed before. We can define the reference period. So users can play around and change a bit the reference period and see how the results are changing. One more cell where we create the paths where we store the data we derive. You can see here how it looks like. And now this part is some, let's say, data consuming a lot of data for this section. So we can see. Don't forget in library. All right. So as I was telling before, we can have this task a bit information, then and of course we try to have some explanations for every cell, so any user, regardless of the level and experience they have, they can understand a bit what's the aim and what can be done. And now let's go to the CI610. So again, what we asked all of you actually for the Mentimeter before, which requires only a couple of megabytes, as Nicholas said previously. So we're gonna take some data from the Met Office of Norway, which they have some time series with the extent for actually Antarctic and the Arctic. And we see here we read some X-rays. Again, like most of the other things, we also used X-rays. It's a very nice library. Make some small processing by removing here some unnecessary variables in our case. We combine all the information in one data set. And here we can plot, for example, the time series. So this is time series of the Arctic and the Antarctic, which they call it CI610. And again, you can see here the results of the first question that we showed also with the animation, that depending on the season, we see essentially that Arctic has less variability. So the lower of Arctic is higher than the lower of the Antarctic. That's why we're season dependent, which the Arctic or Antarctic has more CI610. And now, because for example, we want to make this information about the standardized anomalies, the CIs wanted to make some pre-processing and reformatting the data to have these nice two variables, year and day of the year, so we can play around with climatologies, which, for example, we here by getting the mean value of the CI system. Here now we have some, let's say, auxiliary functions for the plotting, so that can help us, and we can use them all the time for all the similar plots we would like to do. And now we can select the regions, as Nika said before. We try to make it user friendly, to have flexibility to select any region that is available on the data. In this case, for example, it's Antarctic and Arctic for this particular step. And here, for example, we see the picture that was initially, but we have the updated information, right? The most recent data that available from the Norway's methods. So like this, we can have any journalist that wants to have the up-to-date data. For this node, for example, for this particular variable, can get it. But this is the actual time series, and we had in the Mentimeter the question about the standardized values, so how different from the climatology there are. And here we calculate the anomalies by removing the median. We can see here again the plot again up to date, the most recent values. And if we make the standardization, we can answer our question in Mentimeter. So this one is for the Antarctic, and we see that now we have the deviation of around -3. And then we go to the other to see the results. And if I change, so for the Antarctic it was -3. We can run now. Same for the Arctic also. So for the Arctic is around -2, -1. Maybe we have to change it. It's from here. How we change to the to see what we replied, to see the just to see how the group did. They were close.
Okay, but I remember we had like
2.3, something like that. We lost it.
So actually, they lost it too bad.
Not too bad. Maybe we exaggerate a bit in some part. But... How then? We need to have it here. Yeah. So live demo takes a bit of time away, so there are some challenges, but so yeah, this was the result. So we were a bit more extreme on the Arctic and less extreme on the Antarctic, although actually we have a peak for the Antarctic, which is good. So I think we are well informed. That's no, I think it's okay. So pretty much this is what we did. We tried to make also a demonstration of one of the sections of our notebook, and we hope that this work will be used by, let's say, journalists, scientists, and people who would like to transfer the information closer to the policymakers. Yeah.
And also provide feedback. You can always
Definitely.
shoot method, so we're going to maintain it because for the development, in case there's a
We aim to invest time throughout the year for improving this further, so your feedback is very much appreciated. Thank you.
Thank you very much, Niklas. Very impressive work. Maybe there's some questions.
Thanks. Very nice project. I'm not sure if this is a question for you or for the mentors, but are there already plans also to, let's say, disseminate this project and let it be used by some end users because it's really cool.
Yeah, thank you, and congratulations for venturing into the live demo also. You did point out that your target group was the general public, or even worse, the policymakers, which I noted had less scientific literacy than the general public. Have you test-driven that with any of that audience? Have you tried this on people that were in your target group and seen how they responded to it?
Policymakers, of course, like be able to set some material to be used for providing information to the policy, such people, but like journalists in the media, people in the inside the class.
We didn't make that clear, but obviously that no policymaker will do all of this. Whether we're the people like the journalists, they're like there's a dedicated group or department who promote at least in the bigger journalistic houses, where there are people, data scientists who have like some background and environmental science and talk, and sure a bit more to what but yeah, the but yeah, I mean, it would be nice, but we have to do that.
A big sample is important. So if you know some people are in the audience, we can encourage you to share this with some people. Let's see what we can try to do to make it usable.
More questions? We encourage the audience online. Please use a Slido to write your question, and the teams are very willing to answer. Oh, there's one question, isn't it?
So, sorry, like we hear you ask people to do
So from the last question of how if we tested it to the actual target audience, that was the question, I think. So the short answer is no, we did not have the chance to do that yet, but also maybe to just reiterate what I just said, which was probably not clear in the presentation, is that the link to policymakers is indirect and to some of the target group. So we are well aware that no policymaker will go on that Jupyter notebook. But yeah, in the end, we are hoping for getting engagement and feedback on how we can also improve there are like, yeah, some sort of figures questions that pop up frequently, then that would be definitely something we'd like to include in that Jupyter notebook. Yeah.
Very much. The next project is with us. It's called TropiDash, towards a comprehensive tropical cyclone hazard dashboard. Yeah, well, one of the mentors of the project that we have will be Emile Depot. So he will introduce the team and tell us something about the project, the idea.
Okay. Yes, first I would like to say how lucky I feel to have been able to participate to this program for the last 2 years. It's always really nice to see our friendly chat at a coffee machine at ECMWF materialize in the project we are seeing today. It's really great. And the project that I'm going to introduce now, it's the same, but except that it was not a friendly chat at ECMWF, it was at the American Meteorological Society early this year in Denver.
And it was Emma that went to attend the presentation from Sam from the University at Albany in New York State. And the subject was how to use data dashboard to communicate about cyber events. She came out, she said, okay, we need to do a Code for Earth project. We have to find the right people. Then we started looking at ICMWF, which could participate to this challenge. And we immediately said, okay, we're talking about Jupyter Notebook here. Let's talk to Milana. Milana is our expert in Jupyter Notebook, training material using Jupyter. Good to have her with us. We also say, okay, we have to do that with our open data. Emma knows everything about the open data, that's fine. But we also need to know a bit about the data we want to use, and let's do it for tropical cyclone. And let's call Fernando, which knows everything about tropical cyclone data at ICMWF. And then we started, and it was very nice to see few people that were willing to try the challenge. And it was very nice to see how this developed during the summer. And also something I want to stress is that it's a fun part of the Code for Earth, that it still has a summer feeling in this one. And sometimes you have a conference, a visio, where somebody is on a train, you can't hear very well, but it's still very fun to follow and see how the projects is taking shape, and let me show you now. Also, for the mentor, in the next year, I also would like to say that it's very fun to be a mentor because you meet new people, you talk about innovative idea, and Atina and Esperanza, they do everything, all the boring things for you. You just have to help and talk to people. It's really nice. I stop here.
Thank you, Sylvie.
Good afternoon. We will present you our project TropiDash, project towards our comprehensive tropical cyclone analysis data. Our team is made of 3 members, me, Filippo, and Laura. We were mentored by Sylvie, Milana, Fernando, Emma, and Saad. The project purpose arises from some concerns about available products. The available dashboards lack of the interactiveness of plots and charts. They lack the managing products from different sources, and they are usually very for experts users. So our goal was to make something that would also usable for non-expert users. So the main purpose was to build the Jupyter Notebook dashboard to help in preparedness and resilience against tropical cyclone events. So to take a step back, back and make an introduction to tropical cyclones. Tropical cyclones are in turn intense circular storms that originate over warm tropical oceans and are characterized by low atmospheric pressure, high winds, and heavy rain. About 85 tropical storms form annually in the orange areas you see in the map, and they take different names based on the zone they generate. Tropical cyclones are responsible for major hazards as they include and generate natural hazards. Over the past 50 years, more than 1,900 natural disasters are attributed to tropical cyclones. There were more than almost 800,000 persons killed and $1,400 billion in economic losses. So our project started from context recognition, and we found that an ideal dashboard should have not too many variables to avoid confusion, be fast to load, show a basin of interest, or at least zoom in a basin of interest, show summary characteristics about cyclones, display impact layers that can be involved, and represent the intensity category in colors, and have different plots and charts that the user can play around. Then we found out what key variables we wanted to show in our dashboard, and they are all listed here, and we divided them in cyclone properties, meteorological variables, and impact variables. Now I'll leave the word to Laura for purpose.
Good afternoon. Now I'll explain the platform design phase of the project. We use three data sources for the atmospherical variables and the cyclone, for the forecasted atmospherical and cyclone data. We use data from the ECMWF Open Data Catalog. For the observed cyclone data, we use data from EDTracks, which is a complete global collection of cyclone tracks. And for the impact data, we use data from the World Bank Data Catalog. And about the plugins we used, there were many options, all of them, but we at the end decided to work with Voila because of its versatility and compatibility with interactive plots, also because it allowed us to turn the Jupyter Notebook into a standalone application. And also it was very well documented and it was incorporated into the Jupyter project. The dashboard structure is the following. We have 5 sections, one for each type of variables. The first one is dedicated to the cyclone properties. The second one is a visualization of the atmospherical variables. The third one is for the impact variables. And then the fourth one is the joint visualization of the 3 first. And then on the 5th section, we again find the plots of atmospherical data, but now we have the temporal evolution of these variables. And here you can see a scheme of how we go from the open data until the interactive plots. First, we download data using the Azure client, then we format data, and then some additional variables are computed, and then all the maps are created, and the last step is that then the user can interact with the plots. This is the list of the main packages we used in the project. The most important ones are first Voila, which allows us to create a dashboard from a notebook, a Jupyter notebook, and then the 2 libraries of to create widgets, which are the EPI widgets and EP leaflet. And this is the organization of the scripts that we use. First, on one side, we have a folder to store the data that will be downloaded when the dashboard is running. And then we have 5 scripts, which are like libraries specific built for each of the sections. And then we have the backbone notebook, which is the main script that calls all the functions to create each of the sections. And now, Filippo.
Okay, good afternoon, everyone. So the previous group were brave enough to try a live demonstration. We are not. So we did a video to show you a bit around our dashboard, and let's go into it. If internet help us. So we understood live demonstration is better than the video. What should I do?
Okay, now it's nice.
O basta. Okay, sorry for keep you waiting. So you can see this is like the start of the dashboard. It's a Jupyter Notebook in Jupyter Lab. And we have the voila button that opens up our dashboard. So it creates like a web page. In this case, since we're inside Jupyter Lab, it remains there. But if you use your notebook, it will be on the browser. This is a warning message. It was done yesterday morning. No forecast was available for yesterday morning. We select the forecast date, the active storms, and the ensemble members that we want to plot in the forecast tracks of the first section. If you plot less than 5 ensemble members, you can have more information regarding the tracks. The more ensemble you plot, the more heavy your plots is. So we avoided some additional information. Otherwise, the dashboard would crash. You can see there are different layers for section 1. There is the observed track, the average forecast track. And if you zoom in and you go on one of the points, you can see that the day and the percentiles average, like on all the forecast tracks regarding the mean sea level pressure at the center of the cyclone, the wind speed. And the same thing you can consult for the forecast tracks, again, pressure and wind speed information. And also in this section, there is the strike probability map layer, which is information telling you the, let's say, the percentage that, the probability, sorry, that the cyclone will pass over that region in the forecast. So we move to section 2, so to the atmospherical variables. Here we have different variables: pressure, skin temperature, total precipitation. If you look at the mean sea level pressure over there in the bottom in the center, you can see the low pressure center of the cyclone. If you look in the southern part of the North Atlantic. And again, even if you click on total precipitation, you see a lot of the precipitation where the system is.
And the same also for the probability of the meter wind gust over 25 meters per second, very high probability of high wind speed over there where the cyclone actually is. And of course, you can select different time steps to visualize the atmospheric variables, starting with the temporal resolution of 12 hours. This is the impact variables section. You can choose different return period for, in this case, coastal hazard and cyclone hazard. There is a legend explain you a little bit better what these data are actually representing. I won't give too much detail about it. Again, we go full screen, we see all these beautiful layers. We select the one we prefer. We want to look at the population count. So we see that, well, as expected, there's a lot of population in the cities. So New York, Boston, Toronto, and yeah, also in Europe, we have cities. So we move to Europe, and Lisbon has a certain amount of inhabitants. London has a lot of inhabitants. But yeah, now we want to check other stuff. So we want to check the tsunami exposition index. This is an index per country. So we have a color for each country, and it gives you an idea of what's the exposition to tsunamis. Also for coastal floods, we have a similar data, and for sea level rise. For coastal hazard, with a return period of 5 years, we have different colors depending on how high and low is the hazard for that region. We see this for the coast, for the east coast of US. And the same for cyclone hazard, which actually is a raster map. So we zoom a little bit out and we look at the raster map, and very nice palette of colors and telling you, look, here where cyclone happens, so a lot of cyclone hazard. We go to section 4. Section 4 is kind of merging most of the information of the previous section, let's say the most important ones. So we can compare different stuff together, and let's look at the average forecast track together with the cyclone hazard. And yeah, this makes sense. There is a cyclone in the cyclone hazard region. So we can compare these two impact layers information with the actual track of the cyclone. Or for example, coastal hazard, we want to see how is the hazard maybe for an extratropical transition on the coast of Ireland or the coast of the Scotland. And also this information, we can look it together with the track of the cyclone. And last but not least, section 5, so the temporal evolution of the atmospherical variables. Maybe you want to check how the skin temperature or the wind gust over 10 meters evolves during time over the track. We have the average track plotted on the map and a marker to decide which location you want to consult the data. So we move the marker around, and well, we are a little bit undecided. Okay, we select this point, and yes, just a few seconds, the dashboard needs to do its job, and the plots are updated, and we see very nice plots with blue lines telling us wind gust over 25 meters speed. So I didn't show you, but there is also an information button on top of the dashboard. This allows you also to have more idea on what's going on if you need more information. So let's go back to, okay, so we saw a little bit the dashboard how it was developed and now it looks like. Let's just have like a summary debate about what were the challenges we faced and we overcome. So first of all, we had to interact, like all of you, with uncommon data format. It was the first time I was working with buffer data, first time they were working with grid data. So at the beginning, it was a little bit strange. We were with NetCDF, but not NetCDF available for us. We had some, let's say, process to do on the impact variables layer because they were very big, like they're using a lot of memory in the lab, I mean, memory in general. So we had to make them lighter, resampling and adjust them to the projection of the maps we were using. IPI leaflet maps, we had many problems trying to plot rasters on the map. Also because IPI leaflet is a nice package, but it's kind of new. So there is not a lot of documentation regarding, so different trials and errors to understand what exactly we wanted to do. And as well, creating the legends. You saw that we had all the legends together because it was a mess. Actually, Paolo adjusted a repository on GitHub of someone else to be able to do the plots, the maps, the color maps. And but we still weren't able to, change the legend according to the data you're visualizing. Also, package installation was a bit of a problem. A lot of clunky installation process conflicts within the packages, but we managed. And also the computation of strike probability map wasn't that easy. It's one colleague of the NCWF sent me a Python script of 600 lines. And I was like, whoa. And he helped me out a bit, and we managed to adjust this script to our, let's say, application. So we overcome also this. So some of the strengths we want to highlight about our app. So first of all, it's developed in a well-known environment. Everybody who works with Python knows what Jupyter Notebook is, and it's very easy to interact with. It has a very simple access. You can go to our GitHub repository or just click on the badge of Binder and the notebook will open up and you can use the app. It has a simple interface, so Python widgets and IPI widgets and IPI leaflet map, very easy to interact with, and the voila package to launch the dashboard. It groups summary information concerning cycles from different sources. So you see we have a good amount of information available for you to consult regarding tropical cyclones, and as impact variables. So not all the products available online have impact variables in the same place together with the, let's say, forecast of tropical cyclone data. But of course, there are limitations everywhere. So also our dashboard unfortunately has some limitations. We have some limitation about data availability, especially for the impact variables. They are referring to a specific day. They're not like, sorry, for the specific year. They're not up to date, and we will have to do it manually for the next year. So this is something we can adjust, for example. Well, we had no real-time observation for the observed track, but this is like, well, it's very hard to have real-time observation. So we put this just to add a limitation, but I mean, it doesn't really count. We had some limited performance of the Python libraries. As I was saying before, you cannot have all the information displayed when you want to plot 52 ensemble members of the track, because it's a lot of layers going in the map, and IPI leaflet doesn't like it too much. So yeah, this was a little bit of a problem. We had to come up with this agreement of having just information when you plot less than 5 or less cyclone tracks. And we have a little bit of inefficient data download process, because we had to adjust a bit our plots to the grid files and trying to come up with an easier process. But yeah, this was inefficient. Like our process of data download is a little bit inefficient. And following this, so future development, optimized data download. So in the video, the data were already downloaded, but it takes not a lot of time, but it could take less time, and the user can be, let's say, happier to use our dashboard. We want to test other libraries for interactive maps. We reported a few we considered, but then at the end we went for IPI leaflet. We want to be able to consult more data. I reported NOAA. I think everybody knows about NOAA. They have a lot of data available for tropical cyclone activity. Our dashboard can become a partnership between NOAA and NCMWF, and maybe add more data into it. That would be very cool. And dissemination. So you don't know about TropiDash, now you know, tell your friends, check it out. If you also want to discover more things about tropical cyclone data, it's a nice tool to use. So in conclusion, was the project purpose satisfied? This is the project purpose. And yeah, we believe that this purpose was satisfied. We developed a dashboard that is user-friendly, simple to interact with, and even less experienced users that don't know much about meteorology or tropical cyclone are able to work with it. And with that, I'm done. I thank you everyone for your attention. I thank my teammates for having developed this dashboard with me, the mentors that were a great support during all project, NCMWF, the Code for All initiative, Esperanza, Atina. It was a very nice experience. And yeah, if you have any question, we are here, so I'm happy to ask them. Thanks.
Filippo, someone in the lecture room has some question from this team?
Yeah, thanks. It was very nice. Just maybe a silly one. Because you said there are 52 members ensembles, but you plot only the 5. So this is like the 5 first, or it's a random for every?
So you can scroll to the let's say widget, but you can select whatever you like.
Okay, okay.
There is
But it was
the-
only the
Yeah,
5.
exactly. You can choose all the assemble the line.
Yeah. I take the chance if the mic was already here. No, really great stuff. I really enjoyed your presentation and worked smoothly with the video. So I take that also for us for the next time. I wanted to ask if you could start over again, would you make the same choices in terms of voila, like the environments that you have chosen for the dashboard, or would you choose something else? You touched a little bit upon it, but maybe you can elaborate a bit more.
So I think Voila is very nice, very easy to install, and also it's, for example, if you want to implement the dashboard on, put the dashboard on Binder, it's very simple command. You just insert Voila render before your dashboard, then you have it also on Binder. So yeah, I will stick to Voila, but yeah, maybe I will consider better other interactive maps library instead of API leaflet. At the first glance, API leaflet looks very nice, but it has some limitation with handling a lot of information. So yeah, maybe we will try to investigate better other. But yeah, I would recommend Voila for sure.
Then we have in a slider from the online.
Okay, good.
Okay.
Nice.
Thank you very
Nice.
much.
Thanks.
For you. So now we'll have a 30 minutes break. There's coffee break downstairs, in the courtyard. And for the audience online who join remotely, stay tuned because in half an hour, we'll come back. 2 more projects. Thank you. Yes.
Minchia, forse siamo tornati.
so I was fine. I don't wanna go out tonight. All my bones are tired, I'm not looking for a fight. You don't wanna stay home tonight. Is your mind on the outside? She said, should we go where all the people dance? I said, I'd rather go somewhere quieter than that. Some street after midnight. Some street after midnight. Somewhere, somewhere. I get lost by the third bar. Oh, the room is spun, I don't know where you are. And I'm gold in the street light. Take me to the next part. She said, should we go where all the people dance? I said, I'd rather go somewhere quieter than that. Some street after midnight. Some street after midnight. She said, shall I call a cab and take us home? I said, I'd rather go somewhere else and be alone. Some street after midnight. Some street after midnight. Somewhere, so tell me why are we out so late? Rain's coming down in rain. I'd do anything to be by your side, yeah. She said, should we go where all the people dance? I said, I wanna go somewhere quieter than that. Some street after midnight. Some street after midnight. Somewhere. Lay me down. I'm older than I was back then. Too old to lose another friend. To my ego's hungry mouth. Ah, but what can I do when all I really want is you? To know you is to lose you soon. Guess I'll go outside. I guess I'll bide my time. Ooh, ooh, ooh. Ooh, ooh, ooh. Hey. Now, ooh, your words like diamonds hung around my neck. Took your magic everywhere I went. And that silver light was hiding in between our hearts, or even
call you apart. That evening we just talked and talked. I still miss your song. Ooh, ooh, ooh. Just don't take me. Ooh, ooh, ooh. Ooh, ooh, ooh. Ooh, ooh, ooh. Hey.
I'm terrified of sleeping alone, but I can't stay where you are. I don't remember what it's like here without you, but it's time I start. I don't want to, but I still care what you say. It was killing you to watch me be happy, I let you take it away. I tried to make your words mean something that they never meant, but I can't keep shrugging it off. I can't lose any more than I've lost. I wish I had left before you looked down every easy way out, every easy way. Forget how it started, but I remember how it felt. Now it seems like I'm made out of nothing when I'm all by myself. Feel the air push my face as we're swept away with the best of the thoughts that I know I won't say. I'm done tearing myself apart to fill the spaces you left. I tried to make your words mean something that they never meant, but I can't keep shrugging it off. I can't lose any more than I've lost. I wish I had left before you looked down every easy way out, every easy way. Every easy way. I'm so tired of pretending that I'm not afraid.
I know it hurts, but it wasn't meant to last. It was your first, and no, it won't be the last. In the pages of your heart, it's bad, but it'll make you who you are. Carry on with the lessons that they taught, with good intentions that don't mean it's not hard. You loved and lost, and that's alright. Just cry, you don't have to say you're fine. Tell you this won't happen again. Oh, all the pain you're feeling, well, it is what it is. Oh, it's rough, but don't you let it turn you away from love. They were wrong for leaving, but remember that you're enough. I wanna sleep at
And sometime I will do a short wrap up. Then you get to put together a certificate, and you have to get some giveaways. You have probably seen those, but no one did steal one. And then we would like to ask you to go down in the path for that. By the way, the book for the Ruben took before is really nice. But we do also one nice university, and then some interviews. And I would love if you stay all there, do some chatting, discussing, and then we see each other at 9 o'clock and must be real next door. That's the plan for the next one and a half. I hope you have energy. All right, well, I have some exercise so they get more energy, but no. So, I have less energy anymore. Well, the last session, I think.
So now it's a recorded presentation.
Yeah. So we here, so I would also, welcome the audience online back. And again, as mentioned before, use Slido for questions. We have a presentation now that is recorded. So Ayo Patti couldn't make it in person, and he will talk about compression of geospatial data with varying information density. And the mentor is Hauke Schulz, and and Milan Klöver, and they are participating also remotely.
And I would say, let's start.
Yes. Check the room.
Hey everyone, greetings from across the Atlantic Ocean and the Mediterranean Sea. I'm Hauke Schulz and I'm happy to introduce Ayub Fatihi on behalf of the entire Mentor team. Ayub took on the challenge number 12, compressing geospatial data with varying information density. In just a second, he will introduce this subject to you and what that long title actually means. But let me back up a little bit and tell us a bit about ourselves and how this project came about. So we understand that this project is not only a Code for Earth project, but actually also kind of an Earth for Code project, since we are spread over 3 continents, 4 time zones, and up to 8 hours apart. So Ayub Fatihi, our mentee, is joining from Morocco. From the Mentor team, Milan Klöver is joining from the MIT at the US East Coast. Juan Jose Dominguez and Miha Ratzinger from the ECMWF in the UK, and myself joining from the West Coast of the US, the University of Washington. What I really like about this project is how it came along. So, as you might know, we produce more and more data as a society, and climate science is really no exception to it. We always push the envelope and create more and more data, especially with going to higher and higher resolution with our climate simulations. Doing climate simulations myself, I figured that I need a better compression algorithm. Normal, lossless compression algorithms like zip were not up to the task. I needed something more rigorous, something that compresses my data more, and that can only be achieved by lossy compressions. Something like MP4 for music, I needed for climate simulations. Then, while doing some literature research, I came across Milan Klöver's work, and he did a fantastic job in a previous Code for Earth project, where he developed an algorithm that kind of decides what is information in a 2D field and what is not information, what is noise, what can be basically thrown away and doesn't affect the analysis afterwards. So doesn't affect the mean, doesn't affect the gradient of some fields. Basically is similar to throwing away high tones in an MP3 file that the human ear can't hear anyway. So with this being said, I was happy that Milan's algorithm was open source and I could immediately test his algorithm on my own data sets. Connecting then through GitHub with him, we then developed further ideas, and with a colleague of mine, I wrapped his code in my preferred programming language, Python, and that's how we ended up hosting the challenge here for Code for Earth after we developed additional ideas how to even further compress climate simulations, or actually any n-dimensional field really. So by partnering with Code for Earth, these ideas became to life, especially thanks to our mentee, Ayub Fatihi. So for me, this is really a nice success story of open source, and hopefully it encouraged more people to publish and collaborate in the open. But without further ado, please enjoy Ayub's presentation, bringing our ideas to life. Thank you.
Greetings. Thank you for joining me today. I am Ayub. In this year's Code for Earth edition, my focus is on compressing geospatial data with varying information density. I'm grateful for the guidance and supervision provided by Hauke, Milan, Juanjo, and Miha throughout the course of this project. The exponential growth of data across multiple fields has created a demand for efficient data management. According to ECWF, an astonishing 300 terabytes of atmospheric data are being added to the data archive on a daily basis. Also, according to the ECMWF, its data archive is rapidly approaching the exabyte mark. The pressing question is, with this exponential growth, where will the data archive stand in just a few years? Will it enter the Google regime? And furthermore, the graph underscores the critical role of compression. The green dots on the graph represent 10x and 100x compression. So, what is compression? Data compression, also known as source coding or bitrate reduction, relates to encoding information using fewer bits than the original representation. It offers several advantages, including saving storage space, reducing bandwidth requirements, and improving overall system performance. Data compression involves a trade-off between precision, size, and compression speeds. Concerning the precision, it is different than the information content. One example would be someone measuring temperature in his backyard at 6 or 7 or more decimals. It is very precise, but not enough information to get the temperature across the whole city. The goal is to achieve optimal results in all aspects. However, in practice, the aim is to strike a balance that suits the requirements of the application and the available resources. Before getting any further, I want to remind you of how floating numbers are stored in memory. It is actually similar to scientific notation, but in base 2. So the first bit is reserved for the sign. If it is 0, the number is positive. If it is 1, as in this example, the number is negative. The next set of bits represent the biased exponent. It controls how far and in which direction to move the decimal point in the fraction. The bias is a function of number of bits reserved for the exponent. The bias is then subtracted from the calculated exponent to get the biased exponent value, 4 in this case. The remaining bits represent the mantissa, also known as the significand or fraction. These bits represent the fractional portion of the number in binary form. The bitwise real information content-based compression is done as follows. The bitwise information, that is the mutual information between the bits, is calculated. A bit position contains more real information, the stronger the statistical dependence to the adjacent bit is. Then we keep only the bits with real information and discarding the bits with false information. After that, we apply our lossless compression. Before delving into how this compression is implemented, in this plot presented in Clover and Alt's paper, we visualize the compression of water vapor data from the CAMS dataset along the longitudinal dimension. We observe the transition from preserving 100% of information on the left to 83 on the right. The purpose of this demonstration is to showcase the impact of compression, as depicted in the right-hand side. The visual representation appear very pixelated and we start losing data. However, it highlights that you can easily preserve around 100% or 99% of information without sacrificing any crucial details within the dataset. But if we give a closer look to the cartoon land in the right side, near the poles, it is actually not that bad. And this is the motivation to explore adaptive compression on chunks as a challenge for this year. So back to the bitwise real information content-based compression. So we will go through it step by step. So we assume working with graded data from a Cartesian curvilinear or unstructured grids and utilize a binary representation for efficient storage. Then we analyze the mutual information of adjacent bit positions. As an example, let's focus on the sign bit and examine the spatial distribution of all sign bits. When we look at one bit, we inquire about its significance in relation to its neighboring bits, and thus we have more mutual information if the bits have something in common, and less mutual information if the bits just appear randomly. And we do that for the other bits, the exponent bits and mantissa bits, to identify the key bits, which are the significant bits that preserve over 99% of real information or any other wanted percentage. Finally, we remove the false information bits by rounding them to 0, ensuring effective compression without substantial data loss. In this example, we start with a one-dimensional bit stream of data. Using the concept of mutual information, we identify and retain only the significant bits, and the compression can be thought of something like this. And by applying this approach, we compress the data from 160 bits to just 60 bits. To illustrate the bitwise real information context-based compression, I will share example with code. For this, we will be using xbitinfo, which is an X-array wrapper around the bit information GL to retrieve and apply the bit rounding from within Python. The package intends to present an easy pipeline to compress climate datasets based on the real information content. The xbitinfo package is mainly developed and maintained by Hauke Schulz and Aaron Spring. And for bit information GL, it was developed during the summer code editions of the years 2020 and 2021 by Milan Klöver. The dataset used for this example is the 2-meter temperature in Kelvin from the ERA 5 dataset, and the data type is used is float 32. And you can get this data from the Copernicus Climate Data Store. So first thing is getting the information content per bit. For that, we use the get bit information function that calculates the information content for each bit, the sign bit and the exponent bits and the mantissa bits. And as we can see, the first bits contain no real information. Then the values start relatively high and start decreasing near the end. The second step is to discard bits without real information. And to do that, we have to define our key bits that are the number of bits from the mantissa that are necessary to retain approximately 99% of the information or any other percentage we want. In this particular case, the key bits value is calculated to 8 bits. This value is then utilized to round the original data using the XR bit round function. The third step is doing the lossless compression. In this slide, the original size is of 64 megabytes, which can typically be compressed to approximately 34 megabytes, resulting in a compression ratio of 2. However, when compression the bit rounded data, it results of a size of 4.1 megabytes, achieving an impressive compression ratio of approximately 15. So the challenge I have been working on this month is a continuity of the compression method using bitwise real information content that has been developed during last editions of 2020 and 2021 by Milan Klöver. And this year I am working on the development of an information density adapting compression by implementing compression and bit information retrieval on a chunk basis and analyzing the information density of climate variables across space and studying the optimal chunk size depending on specific features like hurricanes. So we have examined the impact of chunking on hurricanes. Using the ERA5 data, we analyzed the Dorian hurricane, like in this case for wind speed variable, and we did not observe any significant differences in the variance of Kippett's value for the chunk where the hurricane occurred. Similar findings can be observed also for the Dorian hurricane using the mean sea level pressure variable. Next, we applied chunking across latitude and longitude on multiple climate datasets. First, we have direct solar radiation. In this plot, we observe the variation in values across latitude and longitude, with high values in Antarctica and null values in the Arctic. And when applying bit rounding to the entire dataset, it employs a total of 12 Kippetts for keeping 99% of the information. By utilizing chunking, we observe a spectrum of Kippett's value, varying from 0 in some chunks, like in the Arctic, to a maximum of 15 in other chunks. Regarding the disk storage utilization for the compression of bit-rounded chunks, it is noteworthy that it has accomplished a storage saving of 59 megabytes compared to the dataset bit-rounded and compressed as a whole. This efficiency is further amplified by the fact that we are retaining higher precision where it is most crucial. Among the other variables we examined, there is convective precipitation. In this plot, value disparities are apparent across latitude and longitude. And the bit rounding across the complete dataset involves utilizing 8 Kippetts to maintain 99% of the information. Chunking reveals a diverse range of Kippetts values, with some chunks containing no Kippetts at all, like in the Antarctica, while others stored as many as 12 Kippetts. And this diversity in Kippetts value underscores the precision with which data is captured through chunking in certain regions. Compression the bit-rounded chunks gives similar results as compression the dataset as a whole, and the chunking strategy proves advantageous by preserving higher precision where it's mostly needed. And we tried to apply chunking on multi-level datasets. In this plot, we are exploring one variable, namely the specific humidity, but at different vertical levels. We can see the variability in values across both latitude and longitude, and also by level. This is shown in the range of values. Like in the subplots A at 1000 hectopascal, namely at the surface of Earth, there are low values in the Arctic and Antarctica, rising smoothly towards the equator. In subplot B at 500 hectopascal, we start seeing the turbulence of the atmosphere all around the globe. In subplot C at 100 hectopascal, some turbulence, but mostly near the equator. And finally, at subplot D, the highest level, we see that the variable is smooth, but just a portion of the Arctic. In this slide, we delve into the variation of keep its distribution among different vertical levels. In the left side, some illustrations to help understand what these vertical levels are like, assuming dry air at a constant temperature. So we have Mount Everest being at almost 9 kilometers at 300 hectopascal. Airplanes flying at 12 kilometers at approximately 200 hectopascals, and the atmospheric balloon at 40 kilometers at approximately 7 hectopascals. So the distribution of Kipits varies depending on the level, with a prime example being the specific humidity variable in the purple color. However, it is important to note that this phenomenon does not hold true for all variables. Take, for instance, the temperature variable in the orange color, which have a consistent distribution across the various levels. So the bitwise, as a summary, the bitwise real information-based compression is executed as follows. First, we calculate the bitwise information and get the key bits. Secondly, we eliminate the bits lacking real information. And finally, we perform the lossless compression. Bit rounding the chunks before compression can enhance the compression by getting more details where needed without taking up more disk storage. And this is my last slide. Thank you for listening.
So thank you, Ayub. I know you are online. I saw you at least. We try to bring you on screen. Wait, I don't want to touch this.
Oh.
Here. Ah, fantastic. So we have Milan
3 times.
3 times. He himself, me, myself, and I, that's good. So we have, okay, and Hauke as well. Yeah. Okay, this twin brother, twin name, and Ayub. Fantastic. So I don't know if you heard the round of applause for you. Yeah, are there any questions in the audience, in the room here? And please, if you're online following the session, write your questions on Slido.
Okay. Hello. Thank you very much for this nice presentation. Oh, yes. Sorry. I'm Johannes Kaiser, and I am a contractor for the CAMS project. I think that was very clear and very neat what you presented, and it's very nice to see how you apply it in more and more sophistication. The whole compression is based on the distinction between real information and not real information, and I'm afraid I wasn't around for the project that introduced this type of distinction. I assume real and non-real information depends on which variable you're looking at, what you assume on smoothness of the field, how it's being calculated, and maybe also which application you're looking at. Can you elaborate a little bit on how you are able to identify unreal information?
Okay, I hope you can hear me.
Can hear you loud and clear.
Yeah, thank you. Yeah, so thank you for your question. So I think I'm very new to this compression, like having the distinction between real information and bit information. So what my answer will be is like it's dependent on the variable, and we need like to calculate the material information that are based on the from the information theory on the entropy and etc. But I think if Milan could take the stage, so he's the expert in this. Thank you.
No, that was already good explanation. Maybe as intuitively, I usually describe it as, imagine you have a data set, and I now go and just take a single bit and flip it from either 0 to 1 or 1 to 0. If I hit a bit that doesn't contain any information, you will even not notice that I've flipped that bit. But for example, if I hit a sine bit and you actually look at temperature, suddenly you have like negative temperature where you had a positive temperature before, and you would absolutely notice the difference. So that is a bit that contains a lot of information, but actually other bits you may not even notice because they're somewhere really down the mantissa, where if you flip a bit, you don't even realize the difference. And that is exactly what the algorithm does. It basically just looks for the surrounding grid points, checks for what are the values, if there's mutual information between them, and then basically decides on whether a bit position contains real or not real information. And really the idea is, because that is different from all the other compression techniques, is that most compression techniques basically say, oh, we try to compress to a certain error. But this one actually tries to compress to a certain amount of information. So it automatically adapts to any kind of variable, level, horizontal region that you want to look at. And this is really the difference. And this is where our use project came from. And this is where he showed, like, there's, especially with some variables, there's a massive difference on where you are, and you should therefore use different precisions to contain that data in a compressed data set.
Thank you. We have another question from Jesper.
Hello, Jesper Dram from ECMWF. I was wondering, so it looked very much like there was less information towards the poles a lot of times. Do you think this would look very differently if you use different grids, for example? I've been thinking too much about adaptive meshes lately, so I doubt a lot of like vertical variability. You would be having like fewer keep bits essentially. Do you have any information on that?
Yeah, so thank you for your question. So this is a hard question for me, but I think for the poles, because of the graded data set, so you have like this from the data set that is uncovered. So the values are like very similar. So yeah, I think yeah. So in the poles, so for some variables, we can consider that they have almost no real information. But yeah, I don't know if Milan, can you, of one of the mentors, Milan or Hauke, can get in more details?
Yeah, I can take over this one. I'm Hauke, although it says Milan, but yeah, this is a very interesting question, and we so far the algorithm that we've written is kind of for a grid where the grid spacing is kind of the same all over the entire grid. So if the grid gets denser at some point, then this measure of entropy kind of also has to be adapted. And yeah, we don't do that currently, but it's definitely something interesting for the future. I hope that answers the question. Are there any further questions? We don't hear anything.
Okay. Can you hear us?
Yeah.
Okay, we are trying to reconnect with the main computer. If you speak, I think they can hear you now.
I can help you. I can connect here. Can you say something? Ayub, I think you should repeat your response.
Okay, so you can hear me now?
Can you? Yes.
Yes, okay. So as Hauke said, like we don't we are not supporting for now when the grid is not very uniform. So yeah, that's it. So yeah, it's it's different to calculate the entropy for if the grid is not as uniform.
Okay. I see a good go from Jesper. Thank you.
Thank you.
Okay, can you hear us?
Okay.
Yes.
Can you hear me? I had a question for Milan because I have been playing with this algorithm last year, and I have a fundamental question about, let's take temperature. If you have a field in Kelvin and you simply convert it to Celsius, so that's just a translation, you suddenly have you go from a field of all negative numbers to a field of negative and positive numbers. And the compression changes. So the compression is not invariant in translation. And that sort of bothers me quite a lot, because the information is exactly the same. But the compression is different. But the information is the same. You just translate by 273.15 the data. So how can you explain that? Same information, different compression.
Yeah, that's a nice example. If you look at the bitwise, like the real bitwise information content spread between sign bit and your very last mantissa bit, and you look at it in terms of Kelvin, you basically don't make use of any of the exponent bits because most of your temperatures will be between 256 and 512. So you kind of have a blob of information sitting somewhere in the mantissa bits. If you now translate it to Celsius, you basically, what you're doing is that you shift this information across bit positions. You retain exactly the same information. However, your key bits will suddenly be at a different place. Yes. Right? So where it was before at, let's say, 10, you may shift it down to 5. Meaning that your technically, but this is a property of the floating point number format, your precision is a different one. However, and this is where your lossless compression algorithm kicks in. The lossless compression algorithm will basically then make sure that the remaining bits are actually compressed away. So in terms of compression factors, we do see very, very similar ones. It just means that the key bits are suddenly different one. But yes, it's exactly as you say, it's the same information because you've just subtracted something.
Okay, thank you very much. Again, thanks for you joining from the East Coast, West Coast. And here we reach the final presentation of the day. And I would like to invite Piero Ferraresi to the stage. Yeah, and the project is not yet ECMWF.
The project has a longer title,
name.
but
The Boba?
yeah, so I think it actually started with Sylvie, but she's been on stage quite a while already. She saw at the American Med Society a nice presentation on how to use this machine learning technologies to look at documentation and find documentation. So we have Giacomo and Piero here. We started to do this very nice project of looking how to use this large language model, mostly ChatGPT, of course, but also you have to look at other open source models and how we can use them to actually find information and also find products on the website. So I will give the floor to Piero now. So thank you very much, Gwen, for mentoring. It was also Sylvie, Hélène, and Miranda, from which the idea started, I guess. Thank you, thanks also to Giacomo, which helped me in building this. Check it out. Okay, so here, this is the original challenge. So using transformer models to develop search engine for datasets, charts, and documentation. Develop a natural language search engine to improve the discoverability of ECMWF datasets, graphical products, and documentation using natural language. So we, okay, this is just the agenda that I will follow. So I will present first the deliverables that we have, then the development strategy that we will, I will try to explain through the example that we will see on the deliverables. And then we have some comments and outlook on the project itself, plus question and answer. So, great introduction. So, exactly. So we kind of, the goal of our project in the end was, despite the long title, was to create a chatbot, that will allow a broad audience of people, so not just technical people, developers, but the general audience to access ECMWF resources in a conversational way, so using natural language. This with the purpose of increase the discoverability and accessibility of the data. So our goal was to create something that was easy to access in conversational style, and that unify also the access to all the different knowledge base and APIs and data that ECMWF has on its servers. So let's give a look at then what's the starting point. So we took then Confluence knowledge base, which is hosted publicly from ECMWF, all the web content which is under ECMWF.int. Then there's some GitHub repositories that we took into consideration, plus the data API and charts API, which are hosted at ECMWF. So these are so quite a lot and diversified unstructured data. Just to have a brief example of how the data may look like. So a Confluence page is something like this. It has a content which contains text and the images and eventually links. The charts API is an open API, is developed with an open API standard, so one can find all the details on how to access API actually through a JSON format, which is quite useful for us for the project, and we will see why later. Then we have the Mectogram API, which with which one can access directly Mectograms, and this, let's say this is just a subset of all the charts API that we have, but so we took this as a nice one to start with, because you can just get the forecast out of that. Then we have the climate data store API, which is huge, has hundreds of parameters and different way of calling them, and can be used through different APIs. And then the web content, which is diversified and it's mostly unstructured text. Plus GitHub repository, in which we loaded also, we use all the, we can access basically all the files that one can find under GitHub. So here we took just a ECMWF API client, and we have EC codes and many others. So then we have, as said, on our GitHub repository hosted on Code4Earth, we have two branches, one using ChatGPT as a large language model that employs the OpenAI API key, which requires subscription. And then we also played with the open source model. In particular, we have a branch that allowed to use very different open source large language models, which are cloud hosted, but with a API which is free, so no pay subscription needed. So we then deploy the software through Docker containers such that people can actually also try and test the application on a normal level. So we don't need to host actually any GPU or server to run all of this. So let's start from the deliverables. No, so from what actually this dashboard produced. So our dashboard is built with Gradio, which is a nice package for building chatbots. No, and here we ask, for example, so the one in blue is our user input, and the answer is from the language model. So we ask a metagram for Venice, and the chatbot replies with an image, which is exactly the one that we wanted. So for the date, so we didn't also not specify any date because it's kind of standard, and the standard will be to produce a metagram with a 10 days forecast out of today date. And this will grab from the Metagram API that we have seen. Another demo is downloading some data. Here we were able to embed the CDS API, the reanalysis data set, so at single level pressure. And here we ask a very broad question, which is download the data for the Hurricane Katrina from the CDS API. And the chatbot allows also for interaction and ask, so whatever data you want for the Hurricane Katrina, are you interested in temperature, precipitation, wind speed, or another type of data? We answer with precipitation, and the chatbot then operates, so requests the data to the API, and then returns the JSON required to make the request. And I let you see that, for example, we ask for precipitation, and the variable in there is, I don't see anymore. Just a second, we have some technical problems. Working again? Yes. Cool. Thank you. So we see that here, so we ask for precipitation. The chatbot is able to interpret that as a proper parameter which exists in the data set. And then, so on top of this, we were able to actually, so the chatbot will autonomously download the data. We were able to add on top a simple plotting routine, which extract from the grid the data and throws that on a map. So this is the result of our query, So this was from Hurricane Katrina, and we were able to generate a map from the grid that show actually so with a time slider that allows to see the evolution over time. So then the other tool that we have at the disposal of this chatbot is the Charts API. Also here, we want to also show how the chatbot is interactive, in the sense that we may also introduce non-technical, so use non-technical language also incomplete. So we ask, for example, a chart of rain in Asia, And the AI responds, could you please specify the time for which you want the chart of rain in Asia? And here I probably misread the question, and I say the whole Asia. And he answered, I understand you want the chart of the whole Asia, however, I need the specific time. In 3 days from now at 16, and he downloads the map. Probably here, so you see is the whole world map, but depending on the query, of course, there are different regions in the Charts API, and probably the one that were best fitting the requests were the whole world. So this is the last tool that we have in our chatbot, and is the knowledge base and documentation. Here we can ask so general user support questions. So show me an example how to retrieve data from the CDS API. And the chatbot will then browse all the documents that are at its disposal, and then will answer, eventually show up a snippet if applicable. And here below we can see that we added the sources that were used to build up this answer. No? So last, then we also added on the dashboard the possibility to give user feedback, which of course is important to actually gather data from the users and understand how to improve certain answers. So this was an overview of all the results that we have with the large language model. And now I will try to explain the two strategies, development strategies that we used for building up this type of products, which seems to be interesting and doing many different things. And we'll use this example to explain so what's happening underneath. No? So first of all, large language models works through prompt engineering. So we supply a certain task to the large language model, which is still a natural language model, which takes as input text and outputs eventually just the next word in the sentence. No? And but are instructed in a certain way that allows to kind of to use different tools. Here, for example, we tell so as a whole, we tell to the large language model that it has at its disposal different tools that's certain to sort of knowledge base code, and then a small description that let the model understands what is the usage for this tool, and then we have other. And then we also need to specify, if applicable, how to call a certain tool. Then here we show that the parameter range needs to specify the latitude, longitude, the station name, eventually for the chart, the valid time, and for the CDS API, and many other different values, no? And then we ask here, so at the end of the prompt, so the way he should format the answer such that we can then further elaborate on the response. So one part, for example, the part of the knowledge base and documentation is based on a concept which is called retrieval augmented generation. So it's a text generation approach that for which there's some data storage in which the text data are stored, and we retrieve the data from there. And there's a generation part which use the retrieved documents to build up new content that makes sense with what was what that is that has coincidence with what was taken from the retrieval phase. So for this, we employ vector databases in which we can store actually numerical representation of images, documents, and audio, and we can query them easily in order to retrieve always, eventually also at a scale with hundreds of thousands of millions of documents in a fast way, so a match for a given query. So we have some models, some transformer models, some embedding model that translate the image, the documents, audio into vector representation, embeddings, which are numerical representation of certain space. Then the user asks for a query that gets embedded as well in a vector representation. Then there's some algorithm that search for matching results between the two. So with these attempts, then we feed so for example, in the example that we have shown, no, we had, so these were the documents retrieved, no, a README with how to use the CDS API, which is coming from the GitHub repository. Retrieve.py file that seemingly was the content of this file was actually making a CDS API request. If you remember in the example I showed, we were asking how to make a CDS API request for data. We have another file from the test directory with the repository. And then we have also another README that explains how to use that through Docker. We feed everything. So whenever the model has understood how to, that he needs to use the knowledge base tool, no?
Then we will submit to it another prompt and we tell him, so use the following piece of context that are attached here below to answer to the question as and try. So we always add on top, if you don't know the answer, just say that you don't know, don't try to make up an answer because you know one of the biggest problems with this type of model are hallucinations. And based on this, then the model generates a new answer. That is the one that we have seen on the example before. Now, to explain the other, so as said, this was the knowledge base and documentation part. For the other tools, the metagram, the charts, and the CDS API download, the approach for that is React, which stands for Reasoning Act. So these large language models like ChatGPT, which is the one that we have used here, can actually interact with itself, given enough tools for doing this. So, and this is the best way of letting to integrate existing API. For example, as said, we have APIs in OpenAPI standard, and that's the best way to have that, or the CDS API as well, or the metric, And this is actually, I think, the cool part of this type of algorithm that can handle these generic queries and integrating with existing tools. So as we have seen, we give it a query. The LLM understand which tool, so understand the inputs. So reason with itself, trying to understand which tool it needs to use, then eventually acts when it has found what to use, and then generates a response based on the response, for example, of the API. So what's the weather like today in Venice? Will be translated into something like this. Understand that it needs a weather forecast for Venice. Search the tool, the API that has that amongst the tools that we have shown at the beginning, the first prompt, and then parse the response to the user. So these actually are the example directly from the query that we asked before regarding the Hurricane Katrina, And these, as before also, so in blue there's the user, and the other is the internal flow of the large language model. So here, so this is not shown to the user, but actually that's what happened underneath. So here the ChatGPT in this respect says the user wants to download data for Katrina from the CDS API. Hurricane Katrina occurred in August 2005, so he probably already knows that because it's a famous event and probably was trained on some data that contains that. He knows the region where that is happening. So, and then he says, I will need to use the CDS API tool to retrieve this data. That recall was one of the tools that we supplied. So the exact parameter will depend on specific data the user wants. I should ask the user to specify the type of data they want. And indeed, we have seen that he asked us what type of data we want. We answered precipitation. It's the first question. He now note down that we want precipitation, and then say, okay, now I know what I need exactly to do. As we told him to use a certain signature for the function for the request, so he knows that he needs to convert that in latitude and longitude, and that's actually a very good thing that ChatGPT does. So you can basically translate a geographical area into latitude and longitude, and then it's applied the year and date as we suggested to him. And the result is what we have seen. So now I'm going towards the end, and I want to share some comments and outlook on this project. So we employed LangChain as a prototyping framework, which is a very, I said, a very nice framework which tries to integrate many different vector database algorithms, strategies for building up large language models tools. So it has been so also once is deployed, it has been relatively easy, to integrate very different things and build the dashboard as you have seen with all the different tools. So as I said, ECMWF has tons of resources, and some of them are indeed difficult to reach. And but the LLM has this ability, if so supplied with the proper data, to understand this interconnection and also reach it to the user. So what we are seeing is, so having structured APIs is extremely useful because then it's easier, you know. Well, structure means open API standards or XML. So structured data that is easy to parse and to aggregate and also to organize, no? Everything that has annotation labels, also in Confluence, for example, there's the labels tags that are helpful to trace back the documents to have kind of keyword searches. So this project was not just we throw all the data to ChatGPT and wait for an answer. That's kind of something that we tried at the beginning, especially. So, so what I want to stress out is that still the solution developed is a prototype, and there's many things that need to be fixed. So, and even though it looks like it can do a lot already, no, there's many different things that need to be processed. So, which is proprietary software. So one needs to pay for that. And in general, for example, we had problems during the development because at the beginning we could not freeze the ChatGPT version. And so over time we had different responses. When we changed it from 3.5 to 4, we actually experienced some queries were not responding anymore as before or not responding at all. Then still, so we uploaded the vector database in June with the Confluence GitHub documents, but also here we need to establish a process on how to update, because when the data are in the vector database, then they are frozen and basically they do not reflect any more updates on the content, whereas in GitHub, in the Confluence and the web-based, all the information are, are continuously changing. And then we need, of course, to monitor model responses because there's so this hallucination are happening. And also we have problems, for example, with formatting answer. So sometimes I will just format the answer in a wrong way that is not processable from the dashboard. So probably, having an open source local model, which is trained and eventually frozen in its state, in its weight, would remove part of the dependency from ChatGPT itself. We tried Llama 2, which is available, as said, in a branch on our repository. It's very so it's yielding very good results. It's fully open source, can run on also on a laptop for certain degrees. And then, so there's already, for example, on GitHub, an awesome link for LLM Ops, which is kind of operation with the LLM, which is, how to actually bring to production this type of model. And now, in the next slide, I will show how complicated that can be. And finally, we stress out that it will be extremely important to do a crowd experiment in which we give the dashboard to many different users at ECMWF and now to gather feedback and to understand what needs to be modified, what can be improved, and to monitor especially the response of the model. So here, as a last slide, so I've found this on a blog post and I found it interesting because so it looks like it's all done by ChatGPT, but actually there's still a lot of job for developers because so there's many, so this type of application comes with many different models in it. So first of all, the embedding models that translate from unstructured data to structured one, so to embeddings. Then there's, for example, we have seen that we have supplied prompts without any type of examples, but actually we could also create agents with a large language model that for which in the prompts there was also example that, for example, how to call a certain API. This example need to be maintained over time. Then the API plugins and whatever that externally that is integrated and changed needs to be reflected. So there needs to be some sort of integration. Then there's caching, validation, logging, and average. So it looks like everything works very smoothly with ChatGPT, but actually there's for bringing this to production, so that it's a whole job, right? So with this, I'm done, and thank you again. So Athena and Esperanza for organizing for Earth, the mentors, and Giacomo, and thank you very much.
Thank you, Piero. Thank you very much for this interesting presentation. And it's the last for today. It has been a long day, but I still would like to give the opportunity to ask questions. Are you still there for answering? Any questions? So,
Oh, yeah. Michael Eisinger from ECMWF. I find it fantastic what you've done. So my question would be, when I'm trying to find an answer to a problem I have, in most of the cases, I find the answer in Jira. So did you consider it, or did you try to use Jira as a source of your training?
So I think that Jira at ECMWF is so there's authorization, it's not public, so I
okay.
cannot use that. So we just employ the open source, fully public information from ECMWF. We also reason at the beginning to use Jira for that, and there was definitely a problem for anonymization of the data because all the tickets and the issues then contain usernames and everything. So it was definitely.
So it's not trivial problem to anonymize the data.
So of course that can be used, but even the idea of having everything open source, we employed only confidence.
Thank you.
But I understand that's a great idea, and actually there's also API to extract the data very easily, so it should be easily done.
Thanks.
Thanks. Yeah. Thanks also for making it look so easy. In your conclusions, one of the comments was that you suggested to use a stable version of the large language model, so that the answers wouldn't change over time. But isn't that partly what you want, so that the model learns from previous exchanges that you have? So wouldn't you throw away that opportunity?
Yeah. So I would say that at the beginning, it will be good to have a uploading state in order to reduce dependency or changing the underlying model, because still, there's some degree of these models are stochastic, so they still are applying not very different, but to some degree of variability. Yeah. And so learning over the new interaction, so that is not done automatically. So still, even having a model like that, so probably ChatGPT is doing something like that, but if we build a model like this, we would need to establish a retraining process, and how to do that exactly. And that's not trivial, but it's also another topic that probably would be much useful for understanding how to improve the usage of such a tool, and also gain information from the user. Yeah, I agree with that.
Have any questions?
Yeah, there are two. Did I understand that the prompts are created by humans to that response? So how big a task you can task this, and how much do you have to go back to?
So yeah, prompts are written from humans. So exactly, for example, LangChain, the framework that we use, has many different prompts already available that one can just plug and play, and that's very easy. But so eventually, changing the model, change also the way the model replies to the answer based on the prompt. No. So for this reason, eventually, over time, with changing data, one would eventually need to update the prompt. And so this probably won't be happening every day, but still over life cycles of months, years, or yes.
And we have the same one for case of interest, we have a meeting situation to the life of the tickets, that topic.
Okay, thank you. Yeah.
Okay, thank you very much.
Yeah, thank you.
We are wrapping up now. Speranza, come here. So it has been a fantastic day. And not only a day, it has been fantastic weeks and months. And I hope we did not bother you too much with all those questions where we received answers or not. So I think it has been a very interesting day today. We learned a lot. We heard a lot of different projects. I hope you're all very happy and satisfied. And I saw that also the teams were, they were mixing. And so that is what we also want to achieve with Code for Earth, the networking part, get in touch with others, spread the word, exchange information and ideas, talk about what could be done next? What do we do with all the data we have and all the projects we started now? So, and I really hope that you continue this over the next couple of hours and also over the next couple of weeks and months. Thanks a lot for everyone. Stay tuned because, we already started to work or have ideas about Code for Earth 2024. It's okay. Spread the word, connect with us on LinkedIn or Twitter if you have not done so. And as said, we have some logistics stuff still.
For dinner today?
Yeah, no, and for the certificate.
Yes, we have the certificates.
And yeah, those we prepared certificates.
Yes, yes.
And Esperanza mentioned this morning. And then before we so I want to thank ECMWF who made this all possible. I want to thank the mentors, the participants, and everyone for participating and made it a great day today. Thank you so much. Oh, and Ruben, and Claudia.
And thank you very much also to all the attendees of the events, those who follow online. And thank you very much. And we will have big news for you very soon. So stay tuned.